Hello there, dear explorer. Welcome back to our quiet corner of wonder, where science meets the gentle rhythm of curiosity. I'm so glad you found your way here tonight. I imagine you might be settling in somewhere comfortable right now, perhaps wrapped in your favorite blanket, or maybe curled up in that special spot where the world feels just a little softer. Wherever you are, you're exactly where you need to be. Tonight, I want to share something beautiful with you, something that's been quietly captivating scientists and dreamers alike, yet remains one of our planet's most guarded secrets. And I have a feeling that by the time we're done exploring together, you'll carry this wonder with you long after you close your eyes. Before we begin this gentle descent, I'd love for you to take a moment, if you'd like, to share what draws you to these mysteries. Leave a comment below, or simply hold that thought close. Our little community of curious souls grows stronger when we share what moves us, and I read every single message you send. So go ahead and let your shoulders drop just a little. Feel your breathing slow to match the pace of our journey tonight. There's no rush here, no urgency, just the quiet pleasure of discovery unfolding like pages in a well-loved book. You know, we spend our lives walking on what feels like solid ground, never truly considering the magnificent secret that lies beneath our feet. Tonight, we're going to explore the hidden world that stretches down, through layers of rock and metal and mystery, to places where diamonds form in chambers of impossible heat, and where the very heart of our planet beats with a rhythm older than time itself. Picture, if you will, our Earth as a gentle giant, sleeping peacefully in the cosmic dark, her surface the soft skin we know, while beneath lies a cathedral of wonders we can only dream of touching, layer upon layer of ancient stories written in stone and flame, each one more extraordinary than the last, each one forever just beyond our reach, like stars reflected in still water. The surface illusion, what lies beneath our feet. Have you ever stood on solid ground and wondered what was really supporting you? Right now, as you listen to this, you're resting on what feels like the most permanent thing in the world, the earth beneath your feet. But here's something beautiful and unsettling. That feeling of solidity is one of the greatest illusions our planet offers us. Imagine for a moment that you could shrink the earth down to the size of an apple. If you did, the part we call solid ground, the crust, where all human civilization exists, would be thinner than the apple's skin. We live our entire lives on this impossibly thin shell, never truly touching the vast alien world that lies just beneath us. When you walk across a field or down a city street, you're actually walking on what geologists call the lithosphere, a brittle, fractured skin that floats like broken eggshell pieces on an ocean of semi-molten rock. It's a bit like living on ice floes in the Arctic, except the ocean beneath isn't water, it's stone, so hot it moves like honey. Currents of rock that have been flowing for millions of years. The surface illusion runs deeper than just the ground beneath our feet. Everything we know about our planet, every mountain, every ocean, every continent, exists in a space so thin that if Earth were a basketball, we'd all be living in a layer thinner than a coat of paint. The deepest ocean trench, the Mariana Trench, reaches down about 11 kilometers. Mount Everest reaches up about 9 kilometers. Our entire world of weather, life and human drama plays out in this narrow band between earth and sky. But what creates this illusion of permanence? Why does something so thin feel so solid? The answer lies in a clever trick of physics and time. The rock beneath us moves, but it moves so slowly that a human lifetime isn't long enough to notice. The continents drift at about the same speed your fingernails grow, roughly 2 centimeters per year. In geological time, they race around the planet like bumper cars, colliding and separating, creating mountains and tearing apart oceans. But in human time, they seem frozen in place. Ancient peoples understood this better than we might think. They built their myths around the idea that the earth was alive, that it could shake and move and change. The Greeks imagined Atlas holding up the world. The Hindus described the earth resting on the back of a giant turtle, swimming through an cosmic ocean. These weren't primitive misconceptions, they were poetic truths about living on a dynamic, moving planet. Modern geology began when scientists started to suspect that this surface stability was an illusion. In the 1600s, people noticed that the coastlines of Africa and South America looked like puzzle pieces that might fit together. But it took until the 20th century for anyone to seriously suggest that continents could move. The idea was so radical, so contrary to our everyday experience of solid ground, that most scientists rejected it for decades. The breakthrough came when we started listening to earthquakes, Every earthquake sends waves rippling through the entire planet, like ringing a bell. These seismic waves travel at different speeds through different materials, and by timing their arrival at stations around the world, scientists could begin to map what lay beneath the surface. What they found was astonishing. The solid Earth was layered, like an onion, with each layer having different properties, different temperatures, different behaviors. That's when the surface illusion truly began to crack. We realized that what we experience as solid ground is actually the cool, brittle skin of a mostly molten planet. Beneath our feet, temperatures rise rapidly. Just a few kilometers down, it's hot enough to melt lead. 100 kilometers down, the rock is so hot, it glows like the heating element in a toaster, kept solid only by the immense pressure from above. The illusion extends to our sense of time as well. When we look at a mountain, we see permanence, but mountains are actually temporary features, rising and falling like waves on an ocean, just over millions of years instead of seconds. The Appalachian Mountains were once as tall as the Himalayas, but time and weather have worn them down to gentle hills. The Himalayas themselves are still growing, pushing skyward as India crashes into Asia in super slow motion. Even the ocean floors aren't permanent. New seafloor is constantly being born at mid-ocean ridges, where molten rock wells up from below and hardens into fresh crust. This new floor spreads outward like a conveyor belt, eventually diving back into the earth at the edges of continents, melting back into the depths from which it came. The oldest rocks on the ocean floor are less than 200 million years old, young by geological standards, because everything older has been recycled back into the depths. This constant recycling means that the earth beneath our feet is not ancient and unchanging, but dynamic and alive. Every atom in the ground around you has probably been to the surface and back to the depths, multiple times over Earth's 4.5 billion year history. The carbon in your body might have once been part of a dinosaur, then limestone on an ocean floor, then erupted from a volcano, then absorbed by a plant you ate for lunch. So, as you stand on what feels like solid ground, remember that you're actually surfing on a thin, cool skin floating on an ocean of molten rock. You're riding continental plates that drift around the planet like massive, slow-moving ships. You're living on the youngest, most dynamic part of a planet that has been recycling itself for billions of years. The surface illusion isn't a flaw in our perception, it's a gift. If we could feel the true dynamism of the Earth beneath us, the constant motion and change, the incredible heat and pressure just kilometers below, we might never be able to sleep peacefully again. Instead, we get to experience the profound comfort of solid ground while living on one of the most dynamic planets in the solar system. And that brings us to our first step into the depths, understanding the crust. This remarkable shell that makes life as we know it possible. Cracked shell. The secrets of the Earth's crust. Think of the last time you dropped an egg. Remember how the shell didn't just break cleanly. It spiderwebbed into a dozen jagged pieces, some large, some small, all fitting together, but slightly separated by hairline cracks. That's essentially what happened to Earth's crust, except the egg was the size of a planet, and the cracks became the boundaries between continents and oceans. The Earth's crust is broken into about 15 major pieces and dozens of smaller ones, all floating on the hot, pliable rock beneath. We call these pieces tectonic plates, from the Greek word tecton, meaning builder or carpenter. It's a fitting name, because these plates are constantly building and rebuilding our planet's surface, like cosmic carpenters working on a project that spans hundreds of millions of years. But here's where the egg analogy breaks down beautifully. Unlike an egg, Earth's crust didn't crack from some ancient impact. It cracked because of what was happening below. Imagine trying to hard-boil an egg while the yolk inside was still boiling vigorously, creating currents and hot spots that pushed against the shell from within. That's closer to what's happening with our planet. The crust comes in two distinct flavors, like a planetary dinner with different courses. Continental crust is thick and light. Relatively speaking, it's made primarily of granite and similar rocks, rich in silicon and aluminum. Scientists sometimes call it SeLoA for short, silicon and aluminum. This continental crust can be up to 70 kilometers thick, in some places, forming massive roots beneath mountain ranges that extend deep into the earth like the hidden part of an iceberg. Oceanic crust is completely different, thin, dense, and dark. It's made mostly of basalt rich in silicon and magnesium, sometimes called simmer. Oceanic crust is rarely more than 10 kilometers thick. but it's much heavier than continental crust. This difference in density is crucial. It's why continents float high like corks on water, while ocean basins sit low and fill with seawater. The boundary between these two types of crust creates some of the most dramatic geography on our planet. Where continents meet oceans, you often find coastal mountain ranges, deep ocean trenches, and chains of volcanoes. These aren't random features, they're the direct result of the crust being broken into moving pieces. When oceanic crust meets continental crust, something remarkable happens. The denser oceanic plate slides beneath the lighter continental plate in a process called subduction. It's like a slow-motion collision between two massive ships, except one ship slides beneath the other and disappears into the depths. As the oceanic plate descends, it begins to melt from the heat and pressure, and some of that molten rock rises back to the surface, creating volcanoes. The Ring of Fire around the Pacific Ocean is the most famous example of this process. From Mount Fuji in Japan to Mount Rainier in Washington state, from the volcanoes of Indonesia to the Andes Mountains in South America, this ring of fire marks the boundaries where oceanic plates are sliding beneath continental ones. These aren't just tourist destinations, they're active workshops where the planet is constantly remaking itself. But not all crustal boundaries involve one plate sliding under another. Sometimes plates slide past each other horizontally, like two trains passing on adjacent tracks. The San Andreas Fault in California is the most famous example of this kind of boundary. The Pacific Plate and the North American Plate are grinding past each other at about 5 centimeters per year, roughly the speed your hair grows. Over millions of years, this has moved Los Angeles nearly 600 kilometers northwest from where it started. The most fascinating crustal boundaries might be the ones where plates are pulling apart. In the middle of the Atlantic Ocean, for example, North America and Europe are slowly separating. New oceanic crust is being born at the Mid-Atlantic Ridge, an underwater mountain range that runs the entire length of the Atlantic like a seam in a baseball. Molten rock wells up from below, hardens into new crust, and pushes the continents apart at about 2 centimeters per year. This means the Atlantic Ocean is getting wider every year, while the Pacific Ocean is getting narrower. If you could travel back 200 million years, you'd find that the Atlantic didn't exist at all. North America and Europe were pressed together in a supercontinent called Pangaea. The dinosaurs lived on a world with completely different geography, where you could walk from New York to Morocco without getting your feet wet. The age of crustal rock tells an incredible story. Continental crust contains some of the oldest rocks on Earth. Ancient granites that formed over 4 billion years ago when our planet was young and very different. These rocks have survived countless collisions, mountain building episodes, and erosion cycles. They're like geological veterans bearing the scars of Earth's entire history. Oceanic crust, by contrast, is always young. The oldest oceanic crust on Earth formed less than 200 million years ago, yesterday by geological standards. This isn't because oceanic crust forms differently, but because it doesn't last. All oceanic crust eventually gets recycled back into the Earth through subduction. It's a conveyor belt system. New oceanic crust forms at mid-ocean ridges, spreads outward, and eventually dives back into the depths at ocean trenches. This recycling system means that the ocean floors are constantly renewing themselves, while the continents accumulate history. Every piece of continental crust carries stories from multiple cycles of ocean opening and closing, mountain building and erosion, climate change and biological evolution. The rocks beneath your feet, if you're on a continent, might have been seafloor when the first fish evolved, then mountain peaks when dinosaurs roamed, then river valleys when mammals first appeared. The thickness variations in the crust create another layer of complexity. Mountain ranges have deep roots. The Himalayan crust extends down 70 kilometers, like a massive iceberg with most of its bulk hidden below the surface. This is why mountain ranges experience what geologists call isostatic rebound. As erosion wears down the mountains, removing weight from the surface, the entire crustal block slowly rises, like a ship rising in the water as cargo is unloaded. The crust also controls where we find different types of rocks and minerals. Diamonds form deep in the mantle, but reach the surface only where latent pieces of continental crust have been stable for billions of years, providing conduits for diamond-bearing rock to rise. Gold often concentrates along the boundaries between different crustal blocks, where ancient collisions created the perfect conditions for ore formation. Perhaps most remarkably, the cracked shell of Earth's crust made life as we know it possible. The movement of crustal plates drives the carbon cycle. burying carbon in ocean sediments and returning it to the atmosphere through volcanic eruptions. This planetary thermostat has kept Earth's climate stable enough for liquid water and life for billions of years. So the next time you feel solid ground beneath your feet, remember that you're standing on one piece of a giant, ancient jigsaw puzzle, a puzzle that's constantly taking itself apart and putting itself back together again, creating and destroying oceans, raising and leveling mountains, and maintaining the delicate balance that makes our planet livable. And beneath this cracked shell lies something even more extraordinary, the mantle, a sea of rock so vast and alien that it contains most of our planet's mass. A sea of rock, journey into the mantle. Close your eyes and imagine honey on a cold winter morning, thick, barely flowing, moving so slowly you can hardly see it happen. Now imagine that honey is made of rock, heated to temperatures that would melt copper, and subjected to pressures that would crush any material we know. Welcome to Earth's mantle, the largest and most mysterious part of our planet. The mantle begins where the crust ends, just a few kilometers beneath your feet, and extends downward for nearly 3,000 kilometers, almost halfway to the center of the Earth. It contains about 84% of Earth's volume and 67% of its mass. If our planet were a peach, the crust would be the skin, the core would be the pit, and everything else, that thick, sweet flesh, would be the mantle. But calling it a sea of rock isn't quite accurate in the way we usually think of seas. The mantle isn't liquid like water or even like molten lava. It's solid rock, but rock that's so hot and under so much pressure that it behaves like an incredibly thick fluid over long periods of time. Geologists call this state plastic, meaning it can flow and deform without breaking, the way silly putty flows if you leave it alone but snaps if you pull it quickly. The temperature in the upper mantle starts at about 1300 degrees Celsius, hot enough to melt copper, and increases steadily with depth. By the time you reach the bottom of the mantle, temperatures approach 4000 degrees Celsius, nearly as hot as the surface of the sun. Yet, despite these incredible temperatures, the rock remains solid because of the immense pressure. It's like trying to boil water at the bottom of the ocean. The pressure keeps it liquid, even at temperatures that would create steam at the surface. This sea of rock is constantly in motion, but motion unlike anything we experience in our everyday lives. Imagine currents in an ocean, but currents that take millions of years to complete one circulation. Hot rock rises from the deep mantle like underwater thermals, reaches the surface, cools, and sinks back down in a process called mantle convection. These convection currents are what drive the movement of tectonic plates on the surface. Our continents and ocean floors are basically just passengers riding on the backs of these deep, slow currents. The composition of the mantle reads like a recipe from an alien cookbook. It's made primarily of silicate minerals, compounds of silicon, oxygen, and various metals like magnesium, iron, aluminum, and calcium. The most common mineral is olivine, a beautiful green crystal that in its pure form is the gemstone paradox. But in the mantle, olivine exists under such extreme conditions that it behaves nothing like the pretty crystals you might see in a jewelry store. As pressure increases with depth, something fascinating happens to these minerals. They undergo phase transitions. Their atomic structure rearranges into denser configurations, like people in a crowded elevator reorganizing to make more room. At about 400 kilometers depth, olivine transforms into a denser mineral called wadsleyite. At about 520 kilometers, it becomes even denser ringwoodite. These transitions create boundaries within the mantle, regions where the properties of rock change dramatically over relatively short distances. The most dramatic of these boundaries occurs at about 670 kilometers depth, where ringwoodite transforms into bridgmanite and ferropericlase minerals. So exotic they weren't even discovered until the 1970s, and can only be created in laboratories using diamond anvil cells that simulate mantle pressures. This boundary is so significant that geologists divide the mantle into upper and lower sections, each with its own distinct behavior and composition. But perhaps the most remarkable thing about the mantle is how we know any of this at all. No human has ever visited the mantle, and no drill has ever reached it. The deepest we've ever penetrated is about 12 kilometers, barely scratching the surface of the upper mantle. So how do we know about this alien realm beneath our feet? The answer comes from the Earth itself, which occasionally sends us samples. Sometimes volcanic eruptions bring mantle rock to the surface in the form of xenoliths, literally foreign rocks, chunks of mantle material that get carried up in rising magma like raisins in bread dough. These xenoliths are windows into the deep earth, allowing us to hold actual pieces of the mantle in our hands and study them in laboratories. but most of our knowledge comes from listening to earthquakes. Every earthquake sends seismic waves rippling through the entire planet, and these waves travel at different speeds through different materials. By measuring how long it takes seismic waves to travel from earthquakes to seismometers around the world, scientists can create three-dimensional maps of the mantle's structure, like using ultrasound to see inside a body. These seismic tomography maps reveal a mantle that's far from uniform. There are hot spots where rock is rising, cold spots where ancient ocean floor is sinking, and structures that suggest the mantle has been stirring itself for billions of years without ever becoming completely mixed. Some regions of the lower mantle appear to contain rock that's chemically different from the rest, possibly remnants of the violent collisions that formed Earth 4.5 billion years ago. The mantle also plays a crucial role in regulating Earth's temperature. It acts like a massive heat engine, transporting thermal energy from the hot interior to the cooler surface. Without mantle convection, Earth would either be a frozen ball of ice or a molten ball of lava. The gradual transport of heat through the mantle helps maintain the temperature range that makes liquid water, and therefore life, possible. Interestingly, the mantle's behavior changes over geological time. When Earth was young, it was much hotter, and mantle convection was more vigorous. This led to more volcanic activity, faster tectonic plate motion, and probably a very different style of surface geology. As the planet has cooled over billions of years, mantle convection has slowed down, and plate tectonics has become more organized and predictable. Some scientists think the mantle might contain as much water as all Earth's oceans combined, locked up in the crystal structure of minerals like ringwoodite. This water isn't liquid, it's hydrogen and oxygen atoms, incorporated into rock crystals. But it could play an important role in how the mantle behaves. The discovery of water-rich ringwoodite in mantle's innerliths has revolutionized our understanding of the deep Earth's water cycle. The mantle also influences the magnetic field that protects us from harmful solar radiation. The motion of the liquid outer core generates Earth's magnetic field, but the pattern of that motion is influenced by heat flow from the mantle above. Changes in mantle convection can affect the magnetic field, and may be responsible for the periodic reversals of Earth's magnetic poles. As we descend deeper into this sea of rock, temperatures and pressures continue to increase, and the minerals become even more exotic. We're approaching a region where the normal rules of matter begin to break down, where pressure becomes so intense that it fundamentally changes how atoms behave. This is the transition zone, where the mantle's deepest secrets are hid. Transition zone, where pressure breaks the rules. Imagine diving to the bottom of the deepest ocean, where the pressure would crush a submarine like an empty soda can. Now imagine going 10 times deeper, then 100 times deeper. Even then, you wouldn't begin to approach the pressures that exist in Earth's transition zone, a mysterious realm 400 to 670 kilometers beneath your feet, where the familiar rules of matter start to bend and break. The transition zone is geology's version of Alice's rabbit hole, a place where normal expectations about how rocks behave simply don't apply. Here, at pressures more than 100,000 times greater than atmospheric pressure, minerals undergo transformations so profound that they become entirely different substances, with different properties, different behaviors, and different ways of interacting with the world around them. To understand what happens in the transition zone, we need to think about pressure in a completely different way than we're used to. At Earth's surface, pressure comes from the weight of our atmosphere, about 15 pounds pressing down on every square inch of your body. It's so gentle and constant that we don't even notice it. But in the transition zone, every square inch bears the weight of hundreds of miles of solid rock pressing down from above. This isn't just more of the same kind of pressure we experience at sea level. This is pressure so intense that it literally squeezes atoms closer together, forcing electrons into different orbital patterns and creating entirely new arrangements of matter. It's as if the fundamental architecture of reality gets remodeled under the weight of an entire planet. The most dramatic transformation in the transition zone involves olivine, the green mineral that makes up most of the upper mantle. At about 400 kilometers depth, something extraordinary happens. The olivine crystals don't just get compressed. They completely reorganize their atomic structure into a denser form called wadsleyite. It's like watching a carefully arranged house of cards suddenly reorganize itself into a completely different structure, all while maintaining the same basic materials. But that's just the beginning here. At about 520 kilometers depth, wadsleyite undergoes another transformation, this time into ringwoodite. And at the bottom of the transition zone, at 670 kilometers depth, ringwoodite breaks down into two completely different minerals, bridgmanite and ferro-pesoclase. Each transformation makes the rock denser, squeezing more matter into the same space. These aren't gradual changes, they're sharp, sudden transitions that create distinct boundaries within the Earth. Seismic waves speed up or slow down dramatically when they cross these boundaries, creating echoes and reflections that seismologists can detect thousands of miles away. It's like the Earth has internal speed bumps made of changing atomic structure. What makes these transformations even more remarkable is that they're completely reversible. If you could somehow bring a piece of ringwoodite to Earth's surface, it would immediately transform back into olivine. The minerals exist in these exotic forms only because of the specific pressure and temperature conditions in the transition zone. It's as if the Earth has created its own laboratory for high-pressure physics, running experiments in mineral behavior that we can barely replicate in our most sophisticated equipment. The discovery of these pressure-induced transformations revolutionized our understanding of how planets work. For decades, geologists thought the boundary between the upper and lower mantle was a chemical boundary, a place where the rock composition changed. But it turns out to be a physical boundary, a place where the same materials reorganize themselves into fundamentally different forms because of pressure alone. This has profound implications for how heat and material move through the Earth. Each transformation releases or absorbs energy, affecting the temperature of the surrounding rock. The boundaries act like filters, allowing some materials to pass through easily while blocking others. Cold, dense slabs of ancient ocean floor might stall at these boundaries for millions of years before finally sinking into the lower mantle. But perhaps the most astonishing discovery about the transition zone came in the 21st century, when scientists realized it might contain vast amounts of water, not liquid water. That's impossible at these temperatures and pressures, but water molecules incorporated into the crystal structure of ringwoodite and wadsleyite. These minerals can contain up to 2.5% water by weight, which might not sound like much until you realize the transition zone might contain more water than all Earth's oceans combined. This water isn't just sitting there, it plays an active role in how the transition zone behaves. Water makes minerals softer and more likely to flow, potentially affecting how heat moves through this region. It might also influence when and how the pressure-induced transformations occur, creating feedback loops that we're only beginning to understand. The existence of so much deep water also raises fascinating questions about Earth's history. Where did all this water come from? How does it move between the surface and the deep interior? Some scientists think the transition zone might act like a massive sponge, absorbing water from descending ocean floor and releasing it when that material eventually rises back toward the surface. Recent discoveries have made the transition zone even more mysterious. In 2014, scientists found the first piece of ringwoodite ever discovered at Earth's surface, trapped inside a diamond that formed in the deep mantle. This tiny speck of mineral, smaller than a grain of rice, contained definitive proof that water exists in the transition zone. The diamond had acted like a time capsule, preserving a sample of deep Earth conditions and carrying it to the surface. The transition zone also affects Earth's magnetic field in ways we're still trying to understand. The pressure-induced transformations change how electrically conductive the rock is, potentially influencing the flow of electric currents that help generate our planet's magnetic field. Some scientists think changes in the transition zone might be connected to the periodic reversals of Earth's magnetic poles. Temperature in the transition zone follows its own strange logic. While it's hot enough to melt most surface rocks around 1500 to 1800 degrees Celsius, the extreme pressure keeps everything solid. But the pressure-induced transformations can create local hotspots where energy is released, or cold spots where energy is absorbed. It's like having a heating and cooling system built into the planet's interior, powered by the weight of rock itself. The transition zone might also explain some puzzling observations about volcanic activity. Some volcanic hotspots, like the one beneath Hawaii, seem to originate from very deep in the mantle, possibly from the core mantle boundary nearly 3,000 kilometers down. But how does hot material rise from such depths without getting stopped by the pressure boundaries in the transition zone? The answer might involve complex interactions between chemistry, pressure, and temperature that we're still working to understand. As we continue our descent through this realm where pressure breaks the rules, we approach an even stranger region, the lower mantle, where rock behaves like putty on a planetary scale, flowing in currents that have been circulating for hundreds of millions of years. Here, The very concepts of solid and liquid begin to lose their meaning. The lower mantle, slow rivers of solid stone. Picture the slowest river you've ever seen, perhaps a lazy summer stream barely moving between its banks, so still you can hardly tell which direction the water flows. Now slow that river down by a factor of 1,000,000,000,000 and turn the water into rock heated to nearly 3,000 degrees. You're beginning to imagine the lower mantle, where solid stone flows like honey through passages wider than continents, carrying the thermal history of our planet in currents that have been circulating since before complex life existed on Earth. The lower mantle begins at the bottom of the transition zone, 670 kilometers down, and extends all the way to the core mantle boundary at 2,900 kilometers depth. It's the largest single region inside our planet, containing more than half of Earth's total mass. If you could hollow it out, it would easily contain all the other planets in our solar system, with room left over for their moons. Down here at pressures more than 250,000 times greater than atmospheric pressure, rock exists in a state that has no equivalent in our everyday experience. It's unquestionably solid. You could theoretically stand on it, if you could somehow survive the crushing pressure and temperature hot enough to vaporize most metals. But over geological timescales, this solid rock flows like a viscous fluid, creating convection currents that rise and fall over hundreds of millions of years. The minerals here are unlike anything found at Earth's surface. The dominant mineral is bridgmanite, a form of magnesium silicate that exists only under the extreme conditions of the lower mantle. Bridgmanite makes up about 70% of the lower mantle's volume, making it the most abundant mineral on Earth by far, even though it was only discovered in the 1970s and has never been found naturally at Earth's surface. Alongside bridgmanite flows ferropetroclase, a dense iron magnesium oxide that gives the lower mantle much of its mass. These two minerals create a kind of rocky soup, flowing together in patterns that persist for hundreds of millions of years. Imagine chocolate and vanilla ice cream swirling together in a bowl, but the bowl is the size of a planet, and the swirling takes longer than the existence of complex life on Earth. The temperature gradient in the lower mantle tells a story of our planet's thermal evolution. At the top, where it meets the transition zone, temperatures hover around 1,800 degrees Celsius. At the bottom, where it meets the outer core, they reach nearly 4,000 degrees, almost as hot as the surface of the Sun. This temperature difference drives the convection that powers plate tectonics at the surface, like a planetary-scale heating system that's been running for billions of years. But the lower mantle isn't just a uniform soup of hot rock. Seismic tomography reveals a complex internal structure, with regions of different temperature, composition, and flow behavior. There are hot upwellings, called superplumes, that rise from the core mantle boundary like massive stone mushrooms. There are cold downwellings where ancient ocean floor, transformed by pressure into dense exotic minerals, sinks like stone snow toward the planet's center. The most mysterious features in the lower mantle are two massive structures that sit on the core mantle boundary beneath Africa and the Pacific Ocean. These large low shear velocity provinces, or LSVPs, are each larger than continents and rise hundreds of kilometers into the lower mantle. They're hotter than the surrounding rock, and possibly chemically different as well. Some scientists think they might be remnants of the ancient magma ocean that covered early Earth, preserved in the deep interior for 4.5 billion years. The flow patterns in the lower mantle connect directly to what we see at Earth's surface. The ring of fire around the Pacific Ocean, the Mid-Atlantic Ridge, the East African Rift. All of these surface features are expressions of deep mantle circulation. Hot upwellings create volcanic hotspots like Hawaii and Iceland. Cold downwellings are marked by deep ocean trenches where old seafloor disappears back into the depths. But the connection between surface and deep mantle isn't simple or direct. Material takes hundreds of millions of years to circulate through the lower mantle. A piece of ocean floor that sinks into a trench today might not return to the surface for 500 million years or more. This means the lower mantle contains a geological record of Earth's entire history, stored in the slow circulation of ancient rock. Recent discoveries have revealed that the lower mantle might not be as dry as once thought. While it contains much less water than the transition zone above it, even small amounts of water can dramatically affect how rock behaves at these extreme conditions. Water makes minerals softer and more likely to flow, potentially creating fast lanes for convection that could speed up the normally glacial pace of mantle circulation. The pressure in the lower mantle is so intense that it creates its own form of chemistry. Atoms are squeezed so tightly together that electrons begin to behave differently, affecting how minerals conduct heat and electricity. Iron atoms can exist in different electronic states, changing the magnetic properties of the rock and potentially influencing Earth's magnetic field generation in the core below. One of the most remarkable aspects of lower mantle convection is its persistence. Individual convection cells, regions where rock rises in one place and sinks in another, can maintain their basic pattern for hundreds of millions of years. This stability is what allows the lower mantle to serve as a kind of geological memory, preserving information about ancient plate configurations and past episodes of volcanism. The lower mantle also acts as a filter for material moving between the upper mantle and the core. Dense materials sink toward the core mantle boundary, while lighter materials rise toward the transition zone. This segregation process has been going on for billions of years, gradually changing the composition of different parts of the mantle and possibly affecting everything from the generation of Earth's magnetic field to the long-term evolution of our atmosphere. Temperature variations in the lower mantle can be surprisingly large. While the average temperature increases steadily with depth, local variations can be several hundred degrees. Hot upwellings can be 800 degrees warmer than cold downwellings at the same depth. These temperature differences drive the convection that ultimately powers plate tectonics, but they also create a complex pattern of heat flow that affects the behavior of the outer core below. The lower mantle's influence on Earth's surface extends far beyond volcanism and plate tectonics. The slow circulation of deep rock helps regulate the planet's long-term carbon cycle, affecting climate over geological timescales. It influences the formation of ore deposits, as rising mantle plumes bring deep materials toward the surface where they can be concentrated by geological processes. As we approach the bottom of this vast region of flowing stone, we encounter one of the most mysterious boundaries in our planet, the D-double prime layer, where the lower mantle meets the outer core. Here, at the deepest reaches of the solid Earth, pressure and temperature reach such extremes that the very nature of matter begins to change in ways we're only beginning to understand. The D layer, the mysterious border to the core. At the very bottom of the mantle, just 2,800 kilometers beneath your feet, lies one of the most enigmatic regions in our entire planet. A zone so strange and mysterious that geologists simply call it the D-double prime layer, using a notation that sounds more like a mathematical equation than a description of actual rock. This thin boundary zone, rarely more than a few hundred kilometers thick, sits at the edge of everything we think we know about solid matter, where rock and metal meet under conditions so extreme they might as well exist on an alien world. Imagine standing at the shore of an ocean, but instead of water lapping at your feet, you're watching liquid iron heated to nearly 4,000 degrees Celsius, as hot as the surface of the sun. Above you stretches not sky, but solid rock also heated to solar temperatures, kept from melting only by pressure so intense it would instantly crush any material we can create. This is the D layer, the boundary between the solid mantle and the liquid outer core, where some of the most important processes on our planet occur in conditions that are completely beyond human experience. The D layer got its unpoetic name from the way seismic waves behave when they reach this depth. In the early days of seismology, scientists labeled different layers based on how earthquake waves traveled through them. The D layer was where they noticed something very strange happening. Seismic waves would slow down, speed up, scatter, and sometimes disappear entirely, as if they were encountering a zone where the normal rules of rock behavior simply didn't apply. What makes the D layer so mysterious is that it's not really one thing, but rather a collection of extreme phenomena, all happening in the same impossibly remote location. It's part solid rock, part liquid metal interface, part chemical reaction zone, and part thermal boundary layer, all rolled into one. Some regions of the D layer are smooth and uniform, while others are rough and chaotic. Some areas are thin, barely 50 kilometers thick, while others bulge upward into the mantle for hundreds of kilometers like massive stone mushrooms. The temperature at the D layer boundary is almost beyond comprehension. We're talking about 4,000 degrees Celsius, hot enough that if you could somehow transport a piece of this rock to Earth's surface, it would glow brighter than molten steel and radiate heat that you could feel from miles away. Yet, despite this incredible temperature, the rock remains solid because of the crushing pressure, nearly 4 million times atmospheric pressure, enough to compress carbon into diamond in milliseconds. At these extreme conditions, minerals behave in ways that defy our everyday understanding. Understanding matter, the bridgmanite and ferropyricles, that make up most of the lower mantle, undergo subtle but important changes as they approach the core boundary. Iron atoms in these minerals can switch between different electronic states, changing their magnetic properties and affecting how they conduct heat and electricity. It's as if the minerals are shape-shifting at the atomic level, transforming into new forms of matter that exist nowhere else in the universe. One of the most significant discoveries about the D layer came from laboratory experiments that recreated these extreme conditions using diamond anvil cells, devices that can squeeze tiny samples between synthetic diamonds while heating them with lasers. Scientists found that at D layer pressures and temperatures, some minerals undergo a phase transition called the post-perovskite transformation. The bridgmanite that dominates the lower mantle transforms into post-perovskite, a mineral so exotic it was only discovered in 2004 and has never been found naturally. This transformation has profound implications for how the D layer behaves. Post-perovskite has different properties than bridgmanite. It's more electrically conductive, has different elastic properties, and deforms in different ways under stress. The transition between the two minerals creates a boundary within the D layer itself, adding another layer of complexity to an already bewildering region. The D layer also serves as a massive thermal boundary layer, like the interface between hot coffee and cool air, but on a planetary scale. Heat from the liquid outer core must pass through this zone to reach the mantle above, but the D layer rock has different thermal properties than the metal below. This creates a complex pattern of heat transfer that influences everything from the generation of Earth's magnetic field to the locations of volcanic hotspots at the surface. Some of the most dramatic features in the D layer are ultra-low velocity zones, regions where seismic waves slow down dramatically, suggesting the presence of partially molten rock. These zones are typically very thin, just a few kilometers thick, but they can extend for hundreds of kilometers horizontally. They might represent places where the boundary between solid and liquid is breaking down, where the extreme conditions are literally melting the bottom of the mantle. The chemical composition of the D layer is another source of mystery. Some scientists think it might be enriched in iron compared to the rest of the mantle, making it denser and more likely to interact chemically with the liquid iron core below. Others suggest it might contain remnants of ancient meteorite impacts, dense material that sank through the mantle billions of years ago and accumulated at the bottom like sediment in a pond. The D layer might also be where some of Earth's most precious metals originated. Platinum, gold and other elements that love to bond with iron are rare in the mantle, but abundant in the core. The boundary zone between mantle and core might be where these elements get concentrated, creating deposits that could eventually be carried back to the surface by rising mantle plumes. Recent research has revealed that the D layer is highly variable from place to place. Beneath some parts of the Pacific Ocean, it's thick and contains massive upwellings that might be the source of volcanic hotspots like Hawaii. Beneath other regions, it's thin and smooth. These variations suggest that the D layer is actively involved in mantle convection, not just a passive boundary between two different layers. The D layer also influences Earth's magnetic field in ways we're still trying to understand. The liquid iron in the outer core generates our planet's magnetic field through a process called the geodynamo, but this process is affected by heat flow patterns at the core mantle boundary. Variations in D layer thickness and composition create variations in heat flow, which in turn affect the motion of liquid metal in the core and the strength and pattern of the magnetic field. One of the most intriguing possibilities is that the D layer might be where major changes in Earth's magnetic field originate. The periodic reversals of our planet's magnetic poles, events that happen every few 100,000 years on average, might be triggered by changes in the D layer that affect core dynamics. Some scientists think the large structures in the D layer beneath Africa and the Pacific might be connected to the current weakening of Earth's magnetic field. The D layer represents one of the final frontiers in Earth science, a region so remote and extreme that we can only study it indirectly through the analysis of seismic waves and high-pressure laboratory experiments. Every new discovery raises more questions than it answers. Is the D layer a single, continuous boundary, or a collection of separate structures? How long do features in the D layer persist? How does material move between the D layer and the core below? As we prepare to cross the ultimate boundary from solid to liquid, from mantle to core, we're about to enter a realm even more alien than anything we've encountered so far. The outer core, a planet-sized ocean of liquid metal that generates the magnetic field, protecting all life on Earth's surface. The outer core, a planet-sized ocean of liquid metal that Imagine an ocean larger than any body of water that has ever existed on Earth's surface, an ocean so vast it could swallow entire continents without leaving a trace. Now imagine that this ocean isn't made of water, but of liquid iron and nickel heated to temperatures that rival the surface of the sun. This is the outer core, the most alien and dynamic environment within our planet. A churning sea of molten metal that lies between 2,900 and 5,100 kilometers beneath your feet. The outer core is almost incomprehensibly large. If you could somehow drain it and place it on Earth's surface, it would form a sphere nearly twice the diameter of the Moon. It contains more metal than all the iron ore ever mined by human civilization, more nickel than exists in all the meteorites that have fallen to Earth, and temperatures so intense that this metal remains liquid, despite pressures that would crush any submarine ever built. To understand how extraordinary this environment is, consider what it takes to melt iron. At Earth's surface, iron melts at about 1500 degrees Celsius, hot enough to glow bright orange and burn through most materials. But in the outer core, pressures are so intense that iron doesn't melt until it reaches nearly 4000 degrees Celsius. The outer core exists in this narrow window, where temperature is high enough to overcome the pressure and keep the metal liquid, creating conditions that exist nowhere else in our solar system. The liquid in the outer core isn't pure iron, though iron makes up about 80% of its composition. The rest is mostly nickel, with small amounts of lighter elements like sulfur, oxygen, and possibly hydrogen. These additions are crucial. They lower the melting point of the mixture and affect its density, creating the specific conditions needed for the outer core to remain liquid while the inner core below it stays solid. This ocean of liquid metal is in constant motion, driven by a combination of forces that create some of the most complex fluid dynamics in nature. Heat rising from the inner core creates convection currents, like the patterns you might see in a pot of boiling water, but scaled up to planetary proportions. The rotation of the Earth adds another layer of complexity, creating spiraling motions and organizing the flow into patterns that can persist for thousands of years. But the motion in the outer core isn't random. It's organized by the same force that makes compass needles point north. The liquid iron is an excellent electrical conductor, and as it moves through Earth's magnetic field, it generates electric currents. These currents in turn strengthen the magnetic field, creating a self-sustaining system called the G-dynamo. It's like a planetary-scale electric generator, powered by heat from below and organized by the rotation of the Earth. The magnetic field, generated by the outer core, is literally a matter of life and death for our planet. This invisible shield deflects most of the high-energy particles streaming from the sun, preventing them from stripping away our atmosphere and sterilizing our surface. Without the outer core's dynamo, Earth would look like Mars, a cold, airless world where liquid water cannot exist on the surface. The complexity of the outer core's motion creates magnetic field variations that we can observe at Earth's surface. The magnetic North Pole isn't fixed. It wanders across the Arctic at speeds of up to 50 kilometers per year, following changes in the deep circulation patterns. Sometimes the entire magnetic field weakens or even reverses completely, with magnetic north and south poles switching places. These reversals happen every few 100,000 years on average, and we might be in the early stages of one right now. Recent discoveries have revealed that the outer core contains structures and motions that weren't predicted by early theories of planetary formation. Seismic waves passing through the outer core reveal evidence of layering regions with different temperatures or compositions stacked on top of each other like layers in a cocktail. There might be a stably stratified layer at the very top of the outer core where lighter elements accumulate and create a barrier to mixing with the mantle above. The boundary between the outer core and the mantle, the same dull layer we explored earlier, is one of the most dynamic interfaces on our planet. Heat flowing from the liquid metal into the solid rock above drives mantle convection and ultimately powers plate tectonics. But this heat flow isn't uniform. It varies from place to place, creating hot spots and cold spots that influence the pattern of circulation in both the outer core and the mantle. Temperature in the outer core varies more than you might expect for a liquid. At the top, where it meets the mantle, temperatures are around 4000 degrees Celsius. At the bottom, where it meets the inner core, they reach nearly 5000 degrees Celsius. This temperature gradient is what drives convection, but it also creates different zones with different flow patterns and different contributions to the magnetic field. The pressure in the outer core ranges from about 1.5 million times atmospheric pressure at the top to over 3 million times atmospheric pressure at the bottom. These are pressures so intense that they affect the fundamental properties of matter. The liquid iron behaves differently than it would at Earth's surface. It's denser, more electrically conductive, and has different thermal properties. One of the most surprising discoveries about the outer core came from studying how seismic waves travel through it. Scientists expected the liquid metal to be relatively uniform, but instead they found evidence of complex structure. There appear to be jets of fast-moving liquid, regions of slower circulation, and possibly even something like weather patterns, storms and currents in liquid metal that last for decades or centuries. The outer core also influences the length of Earth's day in ways that are measurable but tiny. As circulation patterns in the liquid metal change, they alter the distribution of mass within the planet, which affects how fast Earth rotates. These changes are incredibly small, a few milliseconds per century, but they're real and measurable, providing another window into the dynamics of the deep Earth. Chemical reactions at the outer core boundaries add another layer of complexity. At the top, where liquid iron meets solid rock, there might be chemical exchange that changes the composition of both the core and the lowermost mantle. At the bottom, where liquid iron meets solid iron, the crystallization process releases lighter elements that rise through the outer core and affect its circulation patterns. The outer core might also be where some of Earth's water ends up. While most of Earth's water exists at the surface or in the mantle, some hydrogen from water molecules might dissolve into the liquid iron under the extreme conditions of the outer core. This would affect the properties of the liquid and might influence the generation of the magnetic field. Recent computer simulations of outer core dynamics have revealed just how complex this system really is. The circulation patterns involve multiple scales of motion, from small eddies a few kilometers across to planetary-scale currents that span thousands of kilometers. These different scales of motion interact with each other and with Earth's rotation to create the organized flow patterns that generate our magnetic field. As we approach the very center of our planet, we encounter the ultimate boundary, the transition from liquid to solid metal. Here at 5,100 kilometers depth, the outer core gives way to the inner core, a solid sphere of iron and nickel that exists under the most extreme conditions anywhere in our solar system. The dynamo, how a molten sea creates Earth's magnetic shield, deep beneath your feet, deeper than any ocean trench, deeper than the deepest mines. A planetary-scale machine has been running without interruption for billions of years. This machine has no moving parts in the conventional sense, no gears or pistons or turbines, yet it generates one of the most powerful and persistent force fields in our solar system. It's the geodynamo, the process by which the churning ocean of liquid metal in Earth's outer core creates the magnetic field that protects all life on our planet's surface. To understand this invisible shield that surrounds our world, imagine you're holding a simple bar magnet. The magnetic field lines curve from the North Pole to the South Pole, creating an invisible pattern in the space around the magnet. Now scale that up to planetary size, and instead of a solid magnet, imagine the magnetic field as being created by the complex motion of liquid iron in a sphere larger than the planet Mars. That's the geodynamo, a self-sustaining magnetic field generator, powered by the heat of our planet's formation and organized by its rotation. The physics behind the geodynamo is both elegant and incredibly complex. It starts with a simple fact. Liquid iron is an excellent electrical conductor. When this conducting fluid moves through a magnetic field, it generates electric currents, just like a wire moving through the magnetic field of a generator. But here's where it gets interesting. Those electric currents create their own magnetic field, which can strengthen the original field that caused the currents in the first place. This creates what physicists call a positive feedback loop. Motion creates currents. Currents create magnetic fields. Magnetic fields interact with more motion to create more currents, and so on. Under the right conditions, this process becomes self-sustaining, like a river that digs its own channel deeper as it flows. The geodynamo has been running this way for at least 3.5 billion years, and probably much longer. But feedback loops can be tricky things. Without some organizing principle, they tend to either die out completely or run away into chaos. Earth's geodynamo avoids both these fates because of two crucial factors: convection and rotation. Heat rising from the inner core drives convection in the outer core, creating organized patterns of flow. Earth's rotation then twists and organizes these flows into spiral patterns that maintain the magnetic field's basic structure. The Coriolis effect, the same force that makes hurricanes spin and causes water to swirl in different directions in the northern and southern hemispheres, plays a crucial role in organizing the geodynamo. In the outer core, this effect is much stronger than it is at Earth's surface because the liquid is denser and the rotation effects accumulate over much larger distances. The Coriolis effect organizes the chaotic motion of liquid iron into columnar convection cells aligned with Earth's rotation axis. These convection columns are like massive tornadoes made of liquid metal, hundreds of kilometers across and stretching through the entire thickness of the outer core. They rise and fall in complex patterns, carrying heat upward and creating the organized motion needed to sustain the magnetic field. Computer simulations of the geodynamo reveal forests of these metallic tornadoes, all working together to create the invisible shield that protects our planet. The magnetic field generated by the geodynamo isn't constant or uniform. It fluctuates on timescales from years to millions of years, and it's stronger in some places than others. The field is roughly dipolar, meaning it resembles the field of a simple bar magnet, but it has significant multipolar components that create regional variations in field strength and direction. One of the most dramatic variations in Earth's magnetic field is the phenomenon of magnetic reversals. Every few 100,000 years on average, the magnetic field weakens dramatically and then rebuilds with the opposite polarity. Magnetic north becomes magnetic south, and vice versa. During these reversals, which can take thousands of years to complete, the magnetic field becomes chaotic and much weaker, potentially exposing Earth's surface to increased cosmic radiation. The last reversal happened about 780,000 years ago, and some scientists think we might be in the early stages of another one. The magnetic field has been weakening for the past few centuries, and the magnetic North Pole has been moving across the Arctic at increasing speeds. The South Atlantic anomaly, a region where the magnetic field is unusually weak, has been growing larger and stronger. These could be signs that the geodynamo is preparing to flip, but predicting magnetic reversals is incredibly difficult, because the geodynamo is one of the most complex dynamical systems in nature. It involves the interaction of fluid mechanics, thermodynamics, electromagnetism, and planetary rotation, all operating under extreme conditions that we can't directly observe or easily replicate in laboratories. It's like trying to predict the weather, but for a system the size of a planet that operates on timescales of thousands of years. Recent advances in computer modeling have given us new insights into how the geodynamo works. Modern simulations can reproduce many features of Earth's actual magnetic field, including the general dipolar structure, the westward drift of magnetic features, and even some aspects of magnetic reversals. These models reveal that the geodynamo is extremely sensitive to small changes in conditions. A tiny variation in heat flow from the inner core or core mantle boundary can lead to major changes in magnetic field behavior. The strength of Earth's magnetic field has varied dramatically over geological time. During some periods it was much stronger than today, strong enough that compass needles would have pointed in significantly different directions. During other periods, particularly during reversals, it was much weaker, possibly weak enough that high-energy particles from space could have affected Earth's atmosphere and climate. The geodynamo also interacts with the solar wind, the stream of charged particles flowing from the sun in complex ways. When these particles encounter Earth's magnetic field, they're deflected around the planet, creating a teardrop-shaped cavity called the magnetosphere. The boundary of this cavity is constantly moving as the strength of the solar wind varies, creating beautiful phenomena like the aurora, when particles leak through and interact with our atmosphere. Understanding the geodynamo has practical implications beyond pure scientific curiosity. Our modern technological civilization depends on precise navigation systems, satellite communications, and power grids that can all be affected by changes in Earth's magnetic field. Large solar storms can interact with the magnetosphere in ways that disrupt these systems, and the effects are worse when Earth's magnetic field is weak or unstable. The geodynamo also provides clues about the magnetic fields of other planets. Mars once had a strong magnetic field generated by a liquid core, but it disappeared when the planet cooled, and the core solidified. Venus has no magnetic field, despite being nearly Earth's size, possibly because it rotates too slowly to organize core convection properly. Jupiter has an enormous magnetic field, generated by a dynamo in its layer of liquid metallic hydrogen. Studying ancient magnetic fields preserved in rocks, a field called paleomagnetism reveals that the geodynamo has been operating for at least 3.5 billion years, and possibly much longer. This ancient magnetic shield may have been crucial for the development of life on Earth, protecting the early atmosphere from being stripped away by solar wind and cosmic radiation. The energy source for the geodynamo has changed over Earth's history. Early in our planet's evolution, the core was hotter and radioactive decay provided more heat. As the planet cooled, the geodynamo increasingly came to depend on heat released by the crystallization of the inner core, a process that adds energy to the outer core as iron freezes out of the liquid. As we descend toward the very center of our planet, we approach the heart of this magnetic generator, the inner core, a solid sphere of iron and nickel that exists under the most extreme conditions imaginable, where the very concepts of solid and liquid begin to lose their meaning. The inner core, a solid sphere no one can touch. At the very heart of our planet, 6,400 kilometers beneath your feet, lies perhaps the most unreachable place in the entire solar system. Not the surface of the sun, we can at least observe that from a safe distance, not the depths of a black hole, those are impossibly far away, but the inner core of Earth, a solid sphere of iron and nickel about the size of the moon, existing under conditions so extreme that no material technology could ever survive there, no probe could ever reach it, and no human will ever touch it. Yet, this utterly inaccessible realm controls some of the most fundamental aspects of our planet's behavior. The inner core's very existence drives the geodynamo that creates our protective magnetic field. Its gradual growth over billions of years has shaped the thermal evolution of our entire planet. Its mysterious properties, the way seismic waves travel through it, the way it rotates, the way it responds to forces from the outer core, continue to surprise scientists and challenge our understanding of matter under extreme conditions. To understand just how extreme the inner core is, consider the conditions there. The pressure at the center of the Earth is about 3.6 million times atmospheric pressure, roughly equivalent to the weight of the entire atmosphere pressing down on every square inch. The temperature is somewhere between 5,000 and 6,000 degrees Celsius, comparable to the surface of the Sun. Under these conditions, the distinction between solid and liquid becomes almost philosophical. The inner core is solid, in the sense that it has a definite structure and can transmit shear waves, seismic waves that can only travel through solid materials. But it's not solid, the way we normally think of solids. The atoms are packed so tightly together that electrons behave differently than they do under normal conditions. The thermal motion of atoms is so intense that they're constantly vibrating near the limits of their crystal structure. It's solid, but just barely, existing right at the edge of the melting point under crushing pressure. What makes the inner core solid while the outer core remains liquid is a subtle balance between temperature and pressure. As you go deeper into the Earth, both temperature and pressure increase, but they don't increase at the same rate. In the outer core, temperature wins. It's hot enough to keep the iron-nickel alloy liquid, despite the high pressure. But at the very center, pressure finally overcomes temperature, squeezing the atoms so tightly together that they lock into a solid crystalline structure. This crystalline structure is itself a subject of ongoing research and debate. Most scientists think the inner core is primarily composed of hexagonal close-packed iron, a crystal structure where atoms are arranged like cannonballs stacked in the most efficient possible way. But the extreme conditions might create exotic forms of iron that don't exist anywhere else in the universe, phases of matter that we can barely study, even in our most sophisticated high-pressure laboratories. The inner core isn't just sitting there passively, it's growing, very slowly, as heat flows out of the Earth, and the temperature at the core mantle boundary gradually decreases. As the outer core cools, iron crystallizes out of the liquid and freezes onto the surface of the inner core. This process releases latent heat, the same kind of energy that's released when water freezes into ice, and this heat helps drive convection in the outer core above. The growth rate of the inner core is incredibly slow by human standards. Scientists estimate it's growing at a rate of about 1 millimeter per 1,000 years. That means the inner core has been growing for well over 1 billion years, and it will continue growing for billions of years into the future, until the entire core eventually solidifies and our planet's magnetic field disappears. But the inner core's growth isn't uniform. Recent research suggests it might be growing faster on one side than the other, creating an asymmetric structure that affects how seismic waves travel through it. This asymmetric growth might be related to the pattern of heat flow at the core mantle boundary, which isn't uniform around the globe. Areas where more heat flows out of the core might cause more crystallization and faster growth of the inner core. One of the most puzzling aspects of the inner core is how seismic waves travel through it. When earthquakes occur on one side of the planet, some of their seismic waves travel all the way through the Earth and emerge on the other side. By studying these waves, scientists have discovered that the inner core has a complex internal structure with properties that vary in different directions. Seismic waves travel faster through the inner core when they're moving parallel to Earth's rotation axis, from north to south or south to north, than when they're moving in the east-west direction. This anisotropy suggests that the iron crystals in the inner core are aligned in a preferred direction, possibly with their long axes parallel to the rotation axis. But how this alignment developed and what it means for the inner core's formation is still a mystery. Even more mysteriously, there appears to be another layer within the inner core, an innermost inner core that has different seismic properties than the outer part. This inner core is only about 600 kilometers in radius, but it shows a different pattern of seismic anisotropy, suggesting it might have formed under different conditions or at a different time in Earth's history. The inner core also rotates at a slightly different rate than the rest of the planet. This superrotation was discovered by carefully tracking how seismic wave patterns change over time. The inner core appears to rotate about 1 degree per year faster than the surface, completing an extra full rotation about every 360 years. This differential rotation might be driven by magnetic forces from the outer core, or by gravitational interactions with density variations in the mantle far above. But recent studies have complicated this picture even further. Some scientists now think the inner core's rotation rate varies over time, sometimes rotating faster than the surface, sometimes slower, and sometimes even stopping and reversing direction. These changes might be related to variations in the magnetic field generated by the outer core, or to long-term changes in the flow patterns of the geodynamo. The composition of the inner core is another ongoing puzzle. While it's primarily iron and nickel, it must contain some lighter elements to match the density inferred from seismic studies. But which light elements, and in what proportions, remains uncertain. Candidates include carbon, oxygen, sulfur, silicon, and hydrogen. But recreating inner core conditions in the laboratory to test these possibilities is extraordinarily difficult. Recent laboratory experiments using diamond anvil cells and laser heating have begun to shed light on inner core mineralogy. These experiments can recreate pressures and temperatures approaching those at the center of the Earth, revealing that iron behaves very differently under such extreme conditions. The electrical conductivity changes dramatically, thermal conductivity is much higher than expected, and the melting point varies depending on what other elements are present. The inner core's magnetic properties are also puzzling. While the inner core is solid and doesn't contribute directly to the geodynamo, it does affect the magnetic field generated by the outer core. The solid inner core can be magnetized by the field from the outer core, and this magnetization can influence the overall structure and stability of Earth's magnetic field. Some scientists think the inner core might even have its own weak magnetic field, generated by thermoelectric effects, the same principle used in thermocouples to measure temperature. The extreme temperature gradient between the center and edge of the inner core could drive electric currents that create their own magnetic field, though this field would be much weaker than the one generated by the outer core. The inner core represents the ultimate frontier in Earth science, a region so extreme and inaccessible that every piece of information we have about it comes from indirect observations and theoretical modeling. Yet understanding this unreachable realm is crucial for understanding how our planet works, how it formed, and how it will evolve in the future. As we begin our journey back toward the surface, we carry with us a profound appreciation for just how alien and extreme the deep Earth really is. But our exploration of the hidden world beneath our feet is far from over. We still need to understand why, despite all our technology and determination, we can never actually reach these depths ourselves. Why we can't drill deeper. The Kola Superdeep Borehole. In the remote wilderness of Russia's Kola Peninsula, near the border with Norway, stands a small, rusted cap covering what was once humanity's most ambitious attempt to reach the deep Earth. It looks unremarkable, just a metal disc a few feet across, surrounded by abandoned buildings and overgrown vegetation. But beneath that modest cap lies a hole that descends deeper into our planet than any human-made structure has ever gone, 12,262 meters down, barely scratching the surface of the mysteries we've been exploring. The Kola Superdeep Borehole project began in 1970, during the height of the Cold War, when the Soviet Union decided to drill deeper into the Earth than anyone had ever gone before. It was partly a scientific endeavor, partly a technological challenge, and partly a matter of national pride. The goal was ambitious almost to the point of fantasy: drill 15,000 meters down, penetrate the Earth's crust, and perhaps even reach the mantle itself. For 24 years, Soviet scientists and engineers worked to push this narrow hole deeper and deeper into the Earth. They developed new drilling techniques, invented new materials for drill bits and drilling fluid, and solved engineering problems that no one had ever encountered before. The project became a test bed for technologies that would later be used in deep oil and gas drilling around the world. But the Earth fought back in ways no one had anticipated. As the drill descended, it encountered conditions that were far more extreme than anyone had predicted. The temperature at the bottom of the hole reached 180 degrees Celsius, nearly twice the expected temperature. This wasn't just an inconvenience, it was a fundamental barrier. At these temperatures, steel drilling equipment became soft and unreliable. Electronics failed, drilling mud, the fluid used to lubricate the drill bit and carry rock chips to the surface, began to behave more like hot honey than water. The pressure at depth created another set of seemingly insurmountable problems. As the hole got deeper, the weight of rock above began to squeeze the borehole closed. The drilling crew had to constantly fight against the Earth's tendency to heal the wound they were creating. Rock flowed like putty, closing the hole behind the drill bit and trapping equipment thousands of meters below the surface. Perhaps most surprisingly, the deep rocks weren't at all what geologists had expected. Instead of the solid, predictable granite that surface geology suggested should exist at depth, the drilling team encountered rocks that were fractured, water-saturated, and chemically altered by processes that weren't supposed to happen at such depths. They found microscopic plankton fossils at depths where no life was thought to exist. They discovered water at depths where it should have been impossible for water to survive. These discoveries revolutionized our understanding of the deep Earth in ways that justified the entire project, even though it never reached its ultimate goal. The presence of water at great depths suggested that the Earth's crust was much more dynamic and interconnected than anyone had imagined. The fractured nature of deep rocks meant that earthquake processes might work differently than surface observations suggested. The chemical alterations indicated that the boundary between surface and deep processes was much less clear-cut than previously thought. But by 1994, the limitations of drilling technology had become insurmountable. The extreme temperatures and pressures at depth made it impossible to maintain the precision needed for drilling. Drill bits would last only a few hours before failing. The drill string, the long series of connected pipes that carried the drill bit down, would twist and break under the stress. Equipment worth millions of dollars would be lost in the hole, impossible to retrieve. The Kola project taught us that the Earth has natural defenses against our attempts to penetrate it. Unlike drilling through empty space where the main challenge is distance, drilling into the Earth means fighting against increasing temperature, pressure, and chemical reactivity with every meter of depth. It's not just a matter of building stronger equipment. The fundamental physics and chemistry of materials change under these extreme conditions. Temperature is perhaps the most fundamental barrier. As you go deeper into the Earth, temperature increases at a rate of about 25 degrees Celsius per kilometer in most locations. This doesn't sound like much, but it means that at the depth of the lower mantle, 2,800 kilometers down, temperatures would exceed 3,000 degrees Celsius. No material we know how to make could survive these conditions while maintaining the precision needed for drilling. The pressure barrier is equally fundamental. At the bottom of the Kola hole, pressure was about 4,000 times atmospheric pressure. At mantle depths, pressures reach millions of times atmospheric pressure, enough to transform the crystal structure of the drilling equipment itself. Diamond, the hardest natural material, would be compressed into different forms. Steel would behave like putty. Even if we could somehow solve the temperature and pressure problems, there's the issue of the hole itself. A borehole to the center of the Earth would need to be over 12,000 kilometers long, longer than the diameter of the Earth itself. The logistics of managing a drill string of this length are mind-boggling. The weight of the drill string alone would be enormous, creating stresses that no material could withstand. But perhaps the most fundamental barrier is time. Even if we could drill at the record-breaking rate achieved at Kola, about 2 meters per day in the deepest sections, it would take over 16,000 years to reach the center of the Earth. More realistically, accounting for the increasing difficulty with depth, it might take hundreds of thousands of years. No human project has ever been sustained for such timescales. The Kola project also revealed economic barriers that are almost as fundamental as the physical ones. The deeper the hole got, the more expensive each additional meter became. By the end of the project, they were spending enormous amounts of money to advance just a few meters per month. Extrapolating these costs to mantle depths suggests that drilling to the center of the Earth would cost more than the entire global economy produces in a year. Modern drilling projects have pushed deeper than Kola in some specific locations, but they've confirmed rather than overcome the fundamental barriers. The Qatar North Field project has drilled to depths of over 15,000 meters, but only by drilling at an angle and only in carefully selected geological conditions. Deep geothermal projects in places like Iceland have reached depths of several kilometers, but they work by taking advantage of naturally high temperatures near the surface, not by overcoming them. Recent advances in drilling technology have made some progress on the edges of these problems. Better materials can survive higher temperatures for longer periods. Improved drilling fluids can work under more extreme conditions. Advanced computer modeling can help predict and avoid some of the geological surprises that plagued Kola, but these are incremental improvements, not fundamental breakthroughs. Some scientists have proposed alternative approaches to reaching the deep Earth. One idea is to drill through the ocean floor, where the crust is thinner and the distance to the mantle is much smaller. Another is to use existing natural pathways, like volcanic conduits, to place instruments deep in the crust. A few visionaries have even suggested using nuclear explosions to create deep cavities, though the environmental and practical problems with this approach are enormous. But all of these alternatives run up against the same fundamental barriers that stopped Kola. The Earth gets hotter, denser, and more chemically reactive with depth, and these aren't engineering problems we can solve with better technology. They're fundamental limits, imposed by physics and chemistry. The failure to reach the deep Earth through drilling doesn't mean the Kola project was a failure. It provided invaluable scientific data that changed our understanding of deep crustal processes. It pushed drilling technology forward in ways that benefit modern oil and gas exploration. And perhaps most importantly, it taught us humility about the scale and extremity of our planet's interior. The Kola super-deep borehole stands as a monument to human ambition and ingenuity, but also as a reminder of the limits of that ambition. We can send probes to other planets, but we cannot reach the center of our own. We can observe galaxies billions of light years away, but the core of the Earth remains forever beyond our direct reach. And that brings us to one of the most remarkable aspects of Earth science: how we've managed to learn so much about places we can never visit, how we know what's below. Earthquakes as X-rays. Imagine trying to understand the inside of a locked box without ever opening it. You can't see through the walls, you can't drill holes in it, and you can't take it apart. All you can do is shake it gently and listen to how the contents rattle around inside. This might seem impossible, but it's essentially how we've mapped the entire interior of our planet, from the thin crust beneath our feet to the solid iron sphere at the very center. The key to this geological detective work is earthquakes, or more precisely, the seismic waves that earthquakes generate. Every time the Earth shakes, whether from a massive earthquake that destroys cities or a tiny tremor that only sensitive instruments can detect, our planet rings like a bell. These vibrations travel through the entire Earth, carrying information about every layer they pass through, every boundary they cross, and every change in material they encounter. Seismic waves are like X-rays for the planet, but instead of revealing broken bones, they reveal the hidden structure of continents floating on seas of molten rock, the boundaries between solid and liquid deep in the Earth, and the spinning motion of the iron core that generates our magnetic field. The science of seismology reading these planetary vibrations has given us a three-dimensional map of our planet's interior that's more detailed than many maps of the surface. To understand how this works, imagine dropping a pebble into a still pond. The ripples spread outward in circles, carrying energy away from the point of impact. But if there were underwater obstacles in the pond, rocks, logs, changes in depth, the ripples would behave differently. They might speed up or slow down, bend around obstacles, or reflect back toward the source. By watching how the ripples behave, you could map the hidden underwater landscape without ever getting wet. Earthquakes work the same way, but in 3 dimensions and on a planetary scale. When rock breaks deep underground, it releases energy that travels outward as seismic waves. These waves come in several types, each with different properties and behaviors. Primary waves, or P waves, are compression waves that travel fastest and arrive first at seismic stations. They can travel through both solid rock and liquid metal, compressing and expanding the material they pass through like sound waves traveling through air. Secondary waves, or S waves, are shear waves that move more slowly and arrive second. They shake the ground from side to side rather than back and forth, like the motion of a rope being snapped. Crucially, S waves cannot travel through liquids. They require solid material to propagate. This simple fact was the key to one of the most important discoveries in Earth science: the existence of the liquid outer core. In 1906, the Irish seismologist Richard Dixon Oldham was studying records from a large earthquake and noticed something peculiar. On the side of the Earth opposite from the earthquake, there was a shadow zone where S waves simply didn't arrive. It was as if something in the deep Earth was blocking them. Since S waves can't travel through liquids, Oldham concluded that the Earth must have a liquid core. This was the first direct evidence that our planet's interior wasn't solid all the way through. Later refinements to this discovery revealed even more structure. The Danish seismologist Inge Lehmann noticed that some P waves did arrive in what should have been the shadow zone, but they arrived later than expected and from unexpected directions. She realized that these waves must be reflecting off the boundary of a solid inner core within the liquid outer core. This discovery, made in 1936, gave us the basic layered structure of the Earth that we still use today. Modern seismology uses networks of incredibly sensitive instruments scattered across the globe to detect and analyze earthquake waves. These seismometers can detect ground motion smaller than the width of an atom, allowing them to record earthquakes from anywhere on Earth, and even from the Moon and other planets. The global seismographic network has stations on every continent and many islands, creating a planetary-scale listening post for Earth's vibrations. When a large earthquake occurs, seismologists around the world spring into action, not just to assess the damage and aftershock risks, but to use the event as a natural probe of the Earth's interior. Each earthquake provides thousands of seismic ray paths, trajectories that waves take as they travel from the earthquake source to seismometer stations around the world. By measuring how long these waves take to travel and how their properties change along the way, scientists can infer the structure of everything the waves pass through. The process is like medical tomography, where X-rays or other imaging techniques create cross-sectional pictures of the inside of a body. Seismic tomography uses earthquake waves to create three-dimensional images of the Earth's interior, revealing structures from a few kilometers across to continent-sized features in the deep mantle. These seismic images have revealed a planet far more complex and dynamic than early geologists imagined. The mantle isn't a uniform ball of rock. It's full of structures that persist for hundreds of millions of years. There are high-velocity zones where rock is cool and dense, often corresponding to ancient slabs of ocean floor that have sunk into the depths. There are low-velocity zones where rock is hot and less dense, marking rising plumes of material that eventually feed volcanic hotspots at the surface. Some of the most dramatic features revealed by seismic tomography are the large low-shear velocity provinces, or LSVPs, in the deepest mantle beneath Africa and the Pacific Ocean. These massive structures, each larger than a continent and hundreds of kilometers tall, appear to be compositionally different from the surrounding mantle and have been stable for hundreds of millions of years. They might be remnants of the earliest differentiation of the Earth, or they might be the remains of ancient magma oceans, preserved in the deep interior like geological time capsules. Seismic waves have also revealed the complex behavior of the core. The liquid outer core transmits P waves but blocks S waves, confirming its liquid nature. But the waves that do travel through the outer core reveal internal structure, variations in velocity that suggest the liquid metal isn't uniform. There appear to be circulation patterns, possibly even something like weather systems, in the liquid iron. The solid inner core creates its own seismic signature. P waves that travel through it reveal that it's not a simple ball of iron, but has complex internal structure. Waves travel faster when moving parallel to Earth's rotation axis than when moving perpendicular to it, suggesting that the iron crystals are aligned in a preferred direction. There's even evidence for an innermost inner core with different properties, adding yet another layer to our planet's internal structure. But seismic waves don't just reveal structure, they also reveal motion. By carefully tracking how seismic wave patterns change over time, scientists have discovered that the inner core rotates slightly faster than the rest of the planet, completing an extra rotation every few hundred years. They've detected changes in the circulation patterns of the outer core that might be related to variations in Earth's magnetic field. Recent advances in seismic analysis have pushed the resolution of these techniques to remarkable levels. Scientists can now detect and map structures in the mantle just a few kilometers across. They can track the motion of individual convection currents and watch how ancient slabs of ocean floor sink through the mantle over millions of years. They can even detect changes in the deep Earth that occur over human timescales, revealing that our planet's interior is far more dynamic than previously thought. Perhaps most remarkably, seismic waves have revealed that the boundary between different layers in the Earth aren't sharp transitions, but complex zones with their own unique properties. The transition zone between the upper and lower mantle is hundreds of kilometers thick and contains mineral phases that exist nowhere else. The Didi double prime layer at the bottom of the mantle is a complex boundary region where solid rock and liquid metal interact in ways we're still trying to understand. Seismology has also revealed the three-dimensional structure of earthquake zones themselves. showing how stress builds up and releases along fault systems, and how the breakage of rock deep underground creates the shaking we feel at the surface. This understanding has revolutionized earthquake hazard assessment and helped engineers design buildings and infrastructure that can better withstand seismic shaking. As our network of seismic stations grows and our analytical techniques become more sophisticated, we continue to discover new structures and processes in the Earth's interior. Each earthquake, from devastating magnitude 9 events to tiny microquakes that only instruments can detect, adds to our understanding of the hidden world beneath our feet. The fact that we can map the interior of our planet using only the vibrations from earthquakes is one of the most remarkable achievements in science. We've created detailed three-dimensional images of structures thousands of kilometers below the surface using nothing but careful listening and mathematical analysis. It's a testament to human ingenuity and the power of indirect observation. And those observations have revealed that the pressures and forces acting in the deep earth are beyond anything we experience at the surface. The weight of silence. Pressure at the planet's heart. Imagine the weight of the entire atmosphere pressing down on your shoulders. That's 15 pounds per square inch. The pressure we live with every day without even noticing. Now imagine that same pressure multiplied by 10. Your ears would pop. Your body would feel compressed, like diving to the bottom of a swimming pool. Multiplied by 100, and you'd be crushed instantly. Your blood would boil, your bones would shatter like glass. Now multiply that crushing force by 3.5 million. That's the pressure at the center of the Earth. 3.6 million times the weight of our entire atmosphere, pressing inward from every direction simultaneously. It's a pressure so intense that it defies comprehension. A force so overwhelming that it transforms the very nature of matter itself, creating conditions that exist nowhere else in our solar system. To understand pressure at this scale, we need to think about it differently than we normally do. Pressure isn't just a force pressing down from above. It's space itself trying to collapse matter attempting to occupy the same location. The fundamental forces that hold atoms together being overwhelmed by the sheer weight of a planet. At the center of the Earth, every atom is being squeezed from all directions by the gravitational pull of everything above it. This isn't the kind of pressure you get from a hydraulic press or even from the deepest ocean trenches. This is gravitational pressure. The weight of 6,700 kilometers of rock, metal, and everything else that makes up our planet, all trying to fall toward the center at the same time. It's pressure without relief, without escape, building layer upon layer as you descend toward the core. The journey into increasing pressure begins almost immediately as you leave the surface. In the upper crust, pressure increases gradually, about 280 atmospheres per kilometer of depth. This is manageable pressure, the kind deep-sea submersibles are designed to handle. At 10 kilometers depth, you'd experience pressures similar to the deepest ocean trenches, enough to crush an unprotected human body, but not enough to fundamentally change how atoms behave. But as you descend into the mantle, the pressure begins to accumulate in ways that transform matter itself. At 400 kilometers depth, in the transition zone, pressure reaches 40,000 times atmospheric pressure, enough to squeeze olivine crystals into entirely new atomic arrangements. The atoms don't change, but the way they're organized does, creating denser minerals that can exist only under these crushing conditions. By the time you reach the lower mantle, pressure has become a creative force, building new forms of matter that have never existed at Earth's surface. Bridgmanite, the most abundant mineral in our planet, can only form under the extreme pressures of the deep mantle. It's literally a pressure-forged mineral, created by the weight of the Earth itself and stable, only as long as that weight continues to press down from above. The boundary between the mantle and outer core, 2,900 kilometers down, represents a pressure regime that begins to challenge our understanding of how matter behaves. At 1.4 million atmospheres of pressure, the distinction between solid and liquid becomes complex and nuanced. The outer core is liquid, not because it's hot enough to melt at surface pressure, but because even at temperatures approaching those of the sun's surface, the pressure isn't quite enough to lock the iron atoms into a solid crystalline structure. But it's in the inner core where pressure truly reigns supreme. Here at the planet's center, pressure finally overwhelms temperature in the ultimate contest between two fundamental forces. The iron and nickel are hot enough to glow brighter than molten steel, hot enough to vaporize any surface material instantly, yet they remain solid because the pressure is so intense that atoms have no choice but to lock together in the most compact arrangement possible. This pressure creates iron that behaves unlike any iron we know from surface experience. The atoms are squeezed so tightly together that their electron clouds begin to overlap, changing the electrical and magnetic properties of the metal. The crystal structure is probably hexagonal close-packed, the most efficient way to arrange spheres in three-dimensional space. But even this structure is stressed to its limits by the incredible forces acting on it. The pressure in the inner core is so intense that it affects the speed of light traveling through the material. Seismic waves, which are essentially pressure waves themselves, travel faster through the inner core than they would through the same material at lower pressures. The pressure literally compresses space-time itself, creating conditions that exist nowhere else in the accessible universe. But pressure doesn't just affect individual atoms, it affects the behavior of entire regions of the planet. The transition zone in the mantle acts like a pressure valve, with mineral transformations that can either enhance or inhibit the flow of material between the upper and lower mantle. When olivine transforms to wadsleyite, and then to ringwoodite, it releases energy that can drive convection. When ringwoodite breaks down into bridgmanite and ferropyraclase, it absorbs energy, potentially creating barriers to vertical flow. These pressure-driven transformations create feedback loops that affect the entire dynamics of the planet. A cold slab of ancient ocean floor sinking through the mantle will undergo different transformations depending on its temperature and the local pressure conditions. Sometimes these transformations make the slab denser, causing it to sink faster. Sometimes they make it more buoyant, causing it to stall, or even rise back toward the surface. The pressure gradients in the Earth also create what geologists call pressure shadows, regions where the local pressure conditions create unique environments for chemical reactions and phase transformations. These pressure shadows can trap water in the crystal structure of minerals, creating vast reservoirs of H2O in forms that can't exist at surface pressures. The transition zone might contain more water than all the oceans combined, locked away in pressure-stable mineral phases. Pressure also affects how heat moves through the Earth. At high pressures, the thermal conductivity of minerals changes dramatically. Diamond, which is an excellent thermal conductor at surface pressures, becomes even more conductive under the pressure conditions of the deep mantle. This affects how efficiently heat flows from the core to the surface, influencing everything from the generation of the magnetic field to the patterns of volcanic activity. The extreme pressures in the Earth's interior also create opportunities for chemical reactions that are impossible at the surface. Elements that don't normally react with each other can be forced into chemical bonds under high pressure. Water and rock can interact in ways that create entirely new minerals. Carbon can be transformed from graphite to diamond to exotic phases that exist only under extreme pressure. Recent laboratory experiments using diamond anvil cells have begun to recreate the pressure conditions of the Earth's interior, revealing just how dramatically matter behaves under these extreme conditions. At inner core pressures, iron becomes superconductive, potentially affecting how magnetic fields propagate through the deep Earth. The melting point of iron increases so dramatically that it becomes almost meaningless to talk about normal melting behavior. These experiments have also revealed that pressure can create forms of matter that seem to violate our everyday understanding of physics. Ice, for example, can exist in over 20 different solid phases under different pressure conditions, some of which are stable at temperatures well above the normal melting point of water. Similarly, there might be phases of iron in the inner core that are stable only under the incredible pressures at the Earth's center. The pressure at the Earth's center represents more than just a physical extreme. It represents the ultimate limit of how matter can be compressed by gravity alone. Any more pressure would require either more mass or a smaller radius, leading eventually to the formation of a black hole. Our planet exists at the very edge of what's possible for a rocky world, massive enough to create internal pressures that transform matter at the atomic level, but not so massive as to collapse into something even more exotic. Understanding these extreme pressures has practical implications beyond pure scientific curiosity. The materials and processes that exist under high pressure in the Earth's interior might have applications for creating new materials with unique properties. Diamond anvil cell experiments have already led to the discovery of new superhard materials and new forms of matter with unusual electrical and magnetic properties. As we contemplate the silent weight pressing inward at the planet's heart, we begin to understand that pressure is more than just a force. It's a creative principle, a way that matter explores new arrangements and possibilities. And in the deep Earth, this pressure is intimately connected with another fundamental force, heat, that has been building up for billions of years. Heat from the deep, the energy that escapes the core. Beneath your feet, right now, there's a furnace burning at temperatures that rival the surface of the sun. This isn't metaphor or exaggeration. The center of our planet is genuinely as hot as the solar surface, a glowing sphere of iron and nickel that has been radiating heat for over 4 billion years. Every second, our planet releases energy equivalent to thousands of nuclear power plants, heat that flows upwards through thousands of kilometers of rock to eventually warm the ground you're standing on. This geothermal energy is older than life itself, a primordial inheritance from the violent birth of our world. When Earth formed 4.5 billion years ago, it wasn't the cool, solid planet we know today. It was a molten ball of rock and metal, heated by the constant bombardment of asteroids and comets, by the gravitational energy of matter falling together, and by the decay of radioactive elements that were much more abundant in the early solar system. Most of that original heat should have dissipated long ago. Space is cold, -270 degrees Celsius, and heat naturally flows from warm objects to cooler surroundings. By all rights, Earth should have frozen solid billions of years ago, becoming a cold, dead world like Mars. But our planet has remained hot, even increased its internal temperature in some ways because it contains its own internal heating system. The primary source of Earth's ongoing heat production is radioactive decay. Deep within our planet's interior, unstable isotopes of uranium, thorium, potassium, and other elements are constantly breaking apart, releasing energy in the process. This isn't the dramatic, explosive kind of radioactivity we associate with nuclear weapons or reactor meltdowns. It's a gentle, steady process that's been going on since these elements first formed inside dying stars billions of years ago. Uranium-238 has a half-life of 4.5 billion years, meaning that half of the uranium that existed when Earth formed is still here, still decaying, still producing heat. Thorium-232 has an even longer half-life, 14 billion years, which means virtually all the thorium that was present at Earth's formation is still contributing to our planet's heat budget. Potassium-40, with its shorter half-life of 1.25 billion years, was much more abundant in the past and provided more heat to the early Earth. This radioactive heating isn't evenly distributed throughout the planet. Most radioactive elements are incompatible with the iron-nickel alloy that makes up the core, so they concentrate in the rocky mantle and crust. The highest concentrations are often in the continental crust, where granite and other evolved igneous rocks contain unusually high amounts of uranium and thorium. This is why some of the oldest continental rocks are also some of the hottest, still radiating the energy of radioactive decay that began billions of years ago. But radioactive decay isn't the only source of heat in the deep Earth. The core itself generates heat through the crystallization of the inner core. As the planet slowly cools and the boundary between the liquid outer core and solid inner core moves outward, latent heat is released. The same kind of energy that's released when water freezes into ice. But on a planetary scale and involving iron instead of water, this crystallization process is incredibly slow by human standards. The inner core grows by only about a millimeter every 1,000 years. But over geological time, the energy released is enormous. Some scientists estimate that inner core crystallization has contributed more heat to the Earth's interior over the past billion years than radioactive decay has. The heat flow from Earth's interior to its surface averages about 44 trillion watts, roughly 3 times the total energy consumption of human civilization. But this flow isn't uniform around the globe. Some regions, like the mid-ocean ridges where new oceanic crust is formed, have heat flows 10 times higher than the global average. Other regions, like the stable interiors of old continents, have heat flows well below average. These variations in heat flow create the driving force for plate tectonics. Hot spots in the mantle rise toward the surface, creating volcanic activity and new crust. Cool spots sink back into the depths, carrying surface material back into the interior. This convection system has been operating for billions of years, powered by the temperature difference between the hot core and the cool surface. The journey of heat from the core to the surface is an epic tale that spans thousands of kilometers and millions of years. Heat generated by radioactive decay in the lower mantle or released by inner core crystallization must travel through the entire mantle to reach the surface. Most of this journey occurs through conduction, the slow transfer of thermal energy from atom to atom, but some heat travels much faster through convection, carried by the physical motion of hot rock. In the lower mantle, heat conduction is surprisingly efficient. The bridgmanite and ferropericlase that make up most of this region are better thermal conductors than most surface rocks, allowing heat to flow relatively quickly through the solid material. But even quickly is relative. It still takes millions of years for heat to conduct through the lower mantle. The transition zone acts like a thermal filter, with complex effects on heat flow. The phase transitions that occur here, alevine transforming to wadsleyite, to ringwoodite, can either absorb or release heat depending on local conditions. If hot material is rising and undergoing these transformations due to decreasing pressure, the transitions absorb heat and cool the rock. If cold material is sinking and undergoing the reverse transformations due to increasing pressure, heat is released and the rock warms up. In the upper mantle, convection becomes the dominant mechanism for heat transport. Hot rock rises from the depths while cool rock sinks, creating circulation patterns that can persist for hundreds of millions of years. These convection cells carry far more heat than conduction alone could transport, making the upper mantle much more efficient at cooling the deep earth. The crust acts as an insulating blanket, slowing the escape of heat from the interior. Continental crust, with its granite composition and relatively low thermal conductivity, is particularly effective at trapping heat. This is why some of the highest surface heat flows occur through thin oceanic crust, while some of the lowest occur through thick continental crust. But the thermal evolution of the Earth isn't just about heat flowing outward, it's also about how that heat flow has changed over time. Early in Earth's history, when radioactive elements were more abundant and the planet was still cooling from its initial formation, heat flow was much higher than it is today. This drove more vigorous convection in the mantle, faster plate tectonics, and more volcanic activity. The cooling of the Earth over geological time has profound implications for the planet's future. As radioactive elements continue to decay, and the inner core continues to grow, the total heat production of the Earth will gradually decrease. Eventually, perhaps in a few billion years, the planet will cool enough that plate tectonics will shut down entirely. The mantle will become too viscous to convect efficiently, and the surface will become a static, Mars-like shell, but we're nowhere near that point yet. Current estimates suggest that Earth is still producing about half as much heat from radioactive decay as it did when the planet formed. The inner core is still growing, still releasing latent heat. Mantle convection is still vigorous enough to drive plate tectonics and volcanic activity. Our planet remains thermally active and will continue to be so for billions of years into the future. The study of terrestrial heat flow has also revealed unexpected connections between the deep interior and surface processes. Variations in mantle temperature affect the buoyancy of tectonic plates, influencing where mountains form and where ocean basins open. The thermal structure of the deep mantle controls the locations of volcanic hotspots and the chemical composition of volcanic rock. Recent research has even suggested that the Earth's thermal evolution might be more complex than previously thought. Some scientists think the planet might have actually gotten hotter over time in some regions, as radioactive elements became concentrated in certain parts of the mantle. Others suggest that the thermal structure of the deep Earth might undergo periodic reorganizations, with major changes in heat flow patterns occurring over hundreds of millions of years. Understanding terrestrial heat flow also has practical applications. Geothermal energy, which taps into the Earth's internal heat for power generation, depends on understanding where and how heat reaches the surface. Deep geothermal systems might eventually tap into the vast thermal reservoirs of the deep crust and upper mantle, providing a virtually inexhaustible source of clean energy. As we contemplate this vast thermal engine operating beneath our feet, we begin to understand that our planet isn't just a ball of rock floating in space, it's a dynamic, heat-producing system that has been running for billions of years, and will continue running for billions more. And this heat has created environments in the deep Earth that hide some of the most surprising discoveries about our planet. Hidden worlds, subducted continents and buried oceans. Deep beneath Asia, entombed in solid rock and subjected to pressures that would crush diamonds, lie the remains of ancient continents and vanished oceans. These aren't just scattered fragments or geological curiosities, they're entire landscapes, complete ecosystems from Earth's distant past, preserved in the deep mantle like fossils caught in amber. Except instead of amber, they're encased in bridgemanite and ferropetric clays. And instead of being millions of years old, they've been buried for hundreds of millions of years. This hidden world beneath our feet challenges everything we thought we knew about the permanence of geography. The continents we see today, Africa, Asia, North America, aren't the first continents our planet has known. They're the latest in a long series of supercontinents that have assembled and broken apart over Earth's 4.5 billion year history. And when those ancient landmasses were destroyed, they didn't simply disappear, They sank into the depths, creating a geological underworld that preserves the history of our planet's surface. The process begins at the edges of continents, where oceanic plates dive beneath continental margins in subduction zones. Most of the time, the dense oceanic crust sinks smoothly into the mantle, melting and being recycled back into the depths. But sometimes, pieces of the continent itself get dragged down with the sinking ocean floor. Fragments of granite, pieces of ancient mountain ranges, even slices of the continental crust get pulled into the depths and begin their long journey toward the center of the Earth. These subducted continental fragments don't disappear quickly. Continental crust is made of relatively light materials, granite and related rocks that are less dense than the surrounding mantle. Like oil floating on water, continental material tends to rise back toward the surface rather than sink into the depths. But if it gets dragged down far enough and fast enough, it can become trapped in the deep mantle circulation, carried along by convection currents that operate on timescales of hundreds of millions of years. The discovery of these buried continents came from an unexpected source: diamonds. These precious gemstones form deep in the mantle, at depths of 150 to 200 kilometers, under conditions of extreme pressure and temperature. When volcanic eruptions bring diamonds to the surface, they often contain tiny inclusions, microscopic pieces of the mantle minerals that surrounded them during formation. But some diamonds contain inclusions that shouldn't exist at mantle depths. Minerals like quartz, feldspar, and mica, common components of continental crust, have been found trapped inside diamonds, providing direct evidence that continental material had been dragged down to diamond formation depths. These inclusions are like messages from the deep Earth, proof that pieces of ancient continents are scattered throughout the mantle. Seismic tomography has revealed the extent of this continental underworld. Beneath Asia, seismic waves reveal massive structures in the mantle that have the velocity characteristics of continental crust rather than normal mantle rock. These structures extend hundreds of kilometers into the depths and cover areas larger than entire countries. They're the seismic shadows of ancient continents, buried but not destroyed. Some of these buried continents can be linked to specific surface features. The collision between India and Asia that created the Himalayan mountains didn't just crumple the surface, it drove pieces of both continents deep into the mantle. Seismic images reveal what appears to be fragments of ancient Indian continental crust extending down into the transition zone, and possibly beyond. The collision is still ongoing, not just at the surface where the mountains continue to rise, but in the deep mantle where ancient continents continue to sink. But continents aren't the only surface features preserved in the deep Earth. Entire ancient ocean basins have been subducted and now exist as massive structures in the mantle. The Farallon Plate, which once occupied much of the eastern Pacific Ocean, has been almost entirely subducted beneath North America. Seismic tomography reveals the ghostly outline of this vanished ocean as a high-velocity structure extending deep into the North American mantle. These subducted oceans carry with them more than just basaltic crust. They contain sediments from ancient seafloors, water trapped in minerals, and even organic matter from long-extinct ecosystems. Some scientists think the deep mantle might contain more water than all of Earth's surface oceans combined, locked up in the crystal structure of minerals and carried down by subducting slabs. The preservation of water in the deep mantle has profound implications for our understanding of Earth's water cycle. Water that falls as rain today might eventually be carried into subduction zones, pulled down into the mantle, and not return to the surface for hundreds of millions of years. The deep Earth acts like a massive reservoir, storing and slowly recycling water over geological timescales. Recent discoveries have revealed that this deep water cycle is more complex than anyone imagined. Different minerals can store water in different ways and under different conditions. Ringwoodite, the high-pressure form of olivine that exists in the transition zone, can contain up to 2.5% water by weight. If even a small fraction of the transition zone is water-rich, it would contain more water than all the surface ocean. This deep water doesn't exist as liquid. That's impossible at mantle temperatures and pressures. Instead, it's incorporated into the crystal structure of minerals as hydroxyl groups, OH, bonded to other atoms. But despite being chemically bound, this water can still affect how minerals behave. It makes them softer, more likely to deform, and changes their electrical properties. Water-rich regions of the mantle might be fast lanes for convection, allowing material to rise and sink more quickly than in dry regions. The subduction of organic matter raises even more intriguing possibilities. When oceanic plates carrying sediments rich in organic carbon sink into the mantle, that carbon doesn't simply disappear. Some of it might be converted to diamond under the extreme conditions of the deep mantle. Others might react with water to form methane or other organic compounds. The deep earth might be a vast chemical reactor, slowly processing the organic remains of ancient ecosystems. Some scientists have suggested that the deep mantle might even harbor life, not complex organisms like those at the surface, but simple microbes that could survive under extreme conditions of pressure and temperature. These hypothetical deep earth organisms would derive energy from chemical reactions rather than sunlight, and might represent an entirely separate domain of life that evolved independently from surface biology. The chemical signatures of subducted material can be detected in volcanic rocks that erupt at the surface, providing evidence for the recycling of ancient crustal material through the deep mantle. Volcanic rocks from ocean islands like Hawaii contain isotopic signatures that suggest they formed from mantle material that had been contaminated with ancient continental crust. The volcanoes are literally bringing pieces of buried continents back to the surface. The timescales involved in this deep recycling are almost incomprehensible. Material subducted today might not return to the surface for 500 million years or more. This means that the mantle contains a geological record of Earth's entire history, with different regions preserving information about different periods of our planet's evolution. The discovery of these hidden worlds has revolutionized our understanding of how planets evolve. Earth isn't just recycling material at its surface through plate tectonics. It's recycling material through its entire volume, creating connections between surface processes and deep interior dynamics that operate over hundreds of millions of years. This deep recycling might also explain some puzzling observations about Earth's chemistry. Our planet's mantle contains more of certain elements than would be expected if it had formed from the same materials as primitive meteorites. Some of these excess elements might have been added by the subduction of ancient continental crust, carrying with it elements that had been concentrated at the surface through billions of years of geological processes. As we explore these buried landscapes and vanished oceans, we begin to understand that the Earth we see today is just the latest chapter in a much longer story. Beneath our feet lie the remains of ancient worlds, preserved in the deep earth, like pages in a geological book that records the entire history of our planet's surface. And in some of these ancient worlds, life might have found ways to survive in conditions we're only beginning to understand. Life in the deep earth. Microbes that shouldn't exist. 2 kilometers beneath the surface of South Africa, in the suffocating darkness of the Mpunning gold mine, scientists discovered something that challenged our most fundamental assumptions about where life can exist. In water seeping through ancient rock formations, heated to temperatures that should sterilize any living thing, cut off from sunlight for millions of years, they found life. Not just traces of ancient life, not fossilized remains, but living, breathing microorganisms that had been thriving in conditions that seemed utterly hostile to biology. This discovery opened our eyes to the possibility that life on Earth extends far deeper than we ever imagined. Not just in shallow caves or soil, but potentially all the way down through the crust and into the upper mantle itself. The deep subsurface might harbor a hidden biosphere, as large and diverse as all the life we can see at the surface. A shadow ecosystem that operates by completely different rules and derives energy from sources we're only beginning to understand. The microbes found in deep mines don't photosynthesize. There's no sunlight 2 kilometers underground. They don't eat organic matter produced by surface plants. There's no connection to the surface food web. Instead, they've mastered the art of chemosynthesis, deriving energy from chemical reactions involving rock, water, and dissolved gases. They're essentially eating the planet itself, slowly dissolving minerals and using the released energy to power their metabolism. Some of these deep microbes feed on sulfur compounds, breaking down pyrite and other sulfur-bearing minerals and using the energy released by these reactions to build organic molecules from carbon dioxide. Others feed on iron, slowly rusting the ancient metals in rock formations and capturing the energy released in the process. Still others metabolize hydrogen gas produced by the reaction between water and certain types of rock, creating energy from one of the simplest possible chemical reactions. The conditions these organisms survive in are extraordinary by surface standards. Temperatures in deep mines can reach 60 degrees Celsius or higher, hot enough to kill most surface organisms. The pressure is enormous. The pH can be extremely acidic or basic, and toxic metals that would poison surface life are present in high concentrations. There's no oxygen from photosynthesis, and the environment is saturated with radiation from naturally occurring radioactive elements in the rock. Yet, these extreme conditions might actually be advantages for deep life. The high temperatures speed up chemical reactions, potentially providing more energy for metabolism. The pressure helps stabilize certain biological molecules that would be unstable at the surface. The lack of oxygen eliminates one of the most reactive and potentially damaging chemicals that surface organisms have to deal with, and the radiation, rather than being purely destructive, might actually provide an additional energy source through radiolysis, the breaking apart of water molecules by radioactive decay. The discovery of deep life has profound implications for our understanding of the limits of biology. If life can exist 2 kilometers underground in hot, pressurized, chemically hostile environments, how much deeper might it extend? Some scientists think life might exist throughout the entire continental crust, extending down 10 or even 20 kilometers from the surface. That would represent a biomass comparable to all surface life combined. An entire hidden biosphere that we're only beginning to explore. The upper limit for deep life is probably set by temperature rather than pressure or chemistry. Most biological molecules start to break down at temperatures above about 120 degrees Celsius, which occurs at depths of roughly 4 to 5 kilometers in most crustal environments. But even this limit might be flexible. Some organisms use heat-stable proteins and protective mechanisms that allow them to survive at higher temperatures than previously thought possible. Recent discoveries have pushed the depth limits of known life even further. Microbes have been found in drill cores from depths of over 5 kilometers, living in tiny pockets of water within solid rock. These organisms exist at population densities so low that each individual microbe might be separated from its nearest neighbor by meters or even kilometers of solid rock. They reproduce incredibly slowly. Some might divide only once every 1,000 years, and they've been isolated from the surface world for millions or even billions of years. The energy sources for deep life are more diverse than originally thought. In addition to chemical reactions involving rock and water, deep microbes might derive energy from the radioactive decay of uranium, thorium, and other elements in the surrounding rock. This radiolytic metabolism would represent a completely novel way of life, one that uses nuclear decay as a primary energy source rather than chemical reactions. Some deep microbes might even be feeding on organic matter that's far older than anything at the surface. Ancient organic carbon trapped in sedimentary rocks or carried down by subduction could provide energy for deep ecosystems over geological timescales. These organisms would be living on the fossilized remains of ecosystems that existed hundreds of millions of years ago, creating a direct connection between ancient surface life and modern deep life. The isolation of deep microbial communities has led to extraordinary evolutionary divergence. Many deep microbes are only distantly related to surface organisms, suggesting they've been evolving independently for hundreds of millions, or even billions of years. Some represent entirely new branches on the tree of life, with metabolisms and genetic systems that differ significantly from anything found at the surface. This evolutionary isolation might have preserved ancient forms of life that have long since disappeared from the surface. Some deep microbes might be living fossils, representatives of early life forms that evolved before oxygen became abundant in Earth's atmosphere. They could provide insights into what life was like on the early Earth, when the surface was hostile to most forms of biology we're familiar with. The discovery of deep life has also changed our thinking at life on other planets. If microbes can survive kilometers beneath Earth's surface, they might also exist in the subsurface of Mars, Europa, Enceladus, and other worlds that seem inhospitable at their surfaces. The deep subsurface might be the most common habitat for life in the universe, more widespread than the surface biospheres we're familiar with. Deep life might also play important roles in global geochemical cycles. These organisms could be significant players in the carbon cycle, slowly converting organic matter to carbon dioxide over geological timescales. They might affect the formation of ore deposits by concentrating metals through biological processes. They could even influence the chemistry of groundwater and the stability of underground storage sites for carbon dioxide or nuclear waste. The study of deep life has revealed that these ecosystems are incredibly fragile despite their extreme resilience. The organisms reproduce slowly and exist at very low population densities, making them vulnerable to disturbance from mining, drilling, or other human activities. Once disrupted, deep ecosystems might take thousands or millions of years to recover, if they can recover at all. Recent research has also suggested that deep life might be connected to surface life in unexpected ways. Some deep microbes produce methane and other gases that eventually reach the surface, where they can be detected in groundwater or soil gas. This creates a potential pathway for communication between the deep biosphere and surface ecosystems, though the timescales involved are much longer than any biological processes we're familiar with. The biomass of deep life might be enormous. Conservative estimates suggest that the deep subsurface contains at least as much living carbon as all surface plants combined. More optimistic estimates suggest it could be 10 times larger, making the deep biosphere the largest ecosystem on Earth by total biomass, even though it's almost entirely invisible to us. Understanding deep life also has practical implications for human activities. Deep microbes can affect the integrity of underground infrastructure, causing corrosion of pipelines and storage tanks. They can contaminate groundwater with their metabolic products, but they might also be useful for cleaning up contaminated sites, breaking down pollutants in groundwater, or even producing useful chemicals in underground bioreactors. The existence of life at such depths also raises intriguing questions about the origin of life on Earth. Some scientists think life might have actually originated in the deep subsurface rather than at the surface, where it would have been protected from asteroid impacts and ultraviolet radiation that made the early Earth's surface hostile to biology. The deep Earth might not just harbor ancient life. It might be where life first began. As we contemplate this hidden biosphere extending into the depths beneath our feet, we begin to understand that our planet is alive in ways we never imagined. Not just at the surface where we can see forests and coral reefs, but deep in the rock itself where microbes have been quietly living and evolving for billions of years. And this realization leads us to examine some of the more fantastical ideas about what might exist in the deep Earth. The Hollow Earth theory. Science versus fantasy. In 1818, an eccentric American named John Cleves Simmers Jr. published a theory that would capture imaginations for centuries to come. He proposed that the Earth was not a solid ball of rock and metal, but rather a hollow sphere with openings at the north and south poles that led to a vast interior world. This interior, he claimed, was not only habitable, but might be inhabited by unknown civilizations living under a central sun suspended in the hollow core. Simmers' Hollow Earth theory sparked a wave of fascination that extended far beyond scientific circles. Authors like Jules Verne crafted adventure stories about journeys to the center of the Earth. Edgar Rice Burroughs created the fictional land of Pellucidar, a savage world existing on the inner surface of our hollow planet. Even Adolf Hitler was reportedly intrigued by Hollow Earth theories, though this is likely more legend than historical fact. The appeal of a hollow Earth is easy to understand. It promises hidden worlds just beneath our feet, vast unexplored territories that could harbor anything from dinosaurs to advanced civilizations. It suggests that the most exotic adventures don't require traveling to distant stars. They're waiting just below the surface, accessible through secret passages in the polar regions or deep caves. But as romantic as these ideas might be, they collide head-on with everything we know about how planets form, how gravity works, and what the interior of the Earth is actually like. The Hollow Earth theory isn't just wrong. It's wrong in ways that reveal fundamental misunderstandings about the nature of matter, energy, and planetary physics. Let's start with gravity, the force that holds everything together on our planet's surface. Gravity isn't a mysterious force that just happens to pull things downward. It's the result of mass attracting other mass, according to precise mathematical laws discovered by Newton and refined by Einstein. Every atom in the Earth contributes to the planet's gravitational field, and the strength of that field depends on how much mass is pulling on you and how far away that mass is. If the Earth were hollow, with all its mass concentrated in a thin shell, the gravitational field inside that shell would be zero. This isn't a matter of opinion or competing theories. It's a mathematical certainty derived from the basic laws of physics. Inside a hollow sphere, the gravitational forces from different parts of the shell would cancel each other out exactly, leaving anything inside floating weightlessly in the center. This means that Simmers' vision of people walking around on the inner surface of a hollow Earth is physically impossible. There would be no force to hold them to that surface. They would float freely in the center of the hollow space, unable to walk on anything. Even if you could somehow stick to the inner surface, down would point outward toward the shell, and up would point inward toward the center, exactly the opposite of what hollow Earth theories typically describe. The gravitational evidence against a hollow Earth goes beyond theoretical physics. We can measure Earth's gravitational field with extraordinary precision using satellites, and these measurements reveal exactly the mass distribution you'd expect from a solid planet with a dense core and lighter outer layers. If the Earth were hollow, its total mass would be much less than what we observe, and the pattern of gravitational variations around the globe would be completely different. Seismic evidence provides even more definitive proof against hollow Earth theories. Every earthquake sends waves through the entire planet, and these waves behave exactly as you'd expect if they were traveling through solid and liquid materials of varying density. We can track P waves and S waves as they pass through the mantle, reflect off the core-mantle boundary, and travel through the liquid outer core and solid inner core. If the Earth were hollow, seismic waves would show completely different behavior. There would be massive echo chambers, with waves reverberating back and forth across empty spaces. The travel times and paths of seismic waves would be completely different from what we observe. Instead, every earthquake confirms the solid layered structure of the Earth that geology and physics predict. The formation of planets also argues against hollow worlds. When the solar system formed 4.5 billion years ago, Earth grew by the accumulation of countless smaller objects, asteroids, comets, and planetesimals that crashed together under the influence of gravity. This process, called accretion, naturally creates solid, dense objects as material is compressed under its own weight. There's no known mechanism by which planetary accretion could create a hollow world. Gravity always pulls matter inward toward the center of mass, compacting material and increasing density with depth. The intense heat generated by impacts during planetary formation would melt rock and metal, allowing dense materials like iron to sink toward the center while lighter materials float toward the surface. This differentiation process is the opposite of what would be needed to create a hollow planet. The thermal history of the Earth also contradicts hollow Earth theories. Our planet generates heat through radioactive decay and the gradual cooling from its initial formation. This heat has to go somewhere, and it flows outward from the interior to the surface, where it's radiated away to space. If the Earth were hollow, there would be no way to explain the steady flow of geothermal heat we observe at the surface. Modern space exploration has revealed that hollow worlds are essentially unknown in our solar system. Every planet and large moon we've studied shows evidence of being solid throughout, with predictable variations in density based on their composition and formation history. Even small asteroids are typically solid, or at most, loosely aggregated collections of rubble held together by gravity. But perhaps the most straightforward evidence against hollow Earth theories comes from simple density calculations. The Earth's mass is known very precisely from gravitational measurements, and its volume is known from its radius. This gives an average density of about 5.5 grams per cubic centimeter, much denser than typical surface rocks which average about 3 grams per cubic centimeter. This high average density can only be explained by the presence of very dense materials in the Earth's interior, specifically the iron-nickel core that makes up about 30% of the planet's mass. If the Earth were hollow, its average density would be much lower, inconsistent with gravitational measurements. The magnetic field provides another line of evidence against hollow Earth theories. Earth's magnetic field is generated by the motion of liquid iron in the outer core, a process that requires specific conditions of temperature, pressure, and composition that can only exist in a solid planet with a molten metallic core. A hollow Earth could not generate the complex dynamic magnetic field we observe. Despite all this evidence, hollow Earth theories persist in popular culture and fringe science communities. This persistence reveals something important about human psychology and our relationship with the unknown. The idea of hidden worlds beneath our feet appeals to our sense of adventure and discovery, our desire to believe that there are still unknown frontiers waiting to be explored. In a sense, the hollow Earth theory represents a kind of geographic nostalgia, a longing for the days when large portions of the world map were marked. Here be dragons and anything seemed possible in unexplored territories. Now that we've mapped every continent and ocean, the only places left for such fantasies are beneath our feet or beyond the stars. But the real Earth revealed by science is far more fascinating than any hollow world could be. The solid planet we inhabit contains layers of exotic materials existing under conditions more extreme than anything hollow Earth theorists ever imagined. The pressures at the core are millions of times greater than atmospheric pressure. The temperatures rival those at the surface of the sun. The minerals that exist at depth can't be found anywhere at the surface, and some can't even be created in our most sophisticated laboratories. The real journey to the center of the Earth, the intellectual journey we've been taking through seismology, high-pressure physics, and planetary science reveals wonders that dwarf any fictional hollow world. We've discovered seas of liquid metal generating magnetic fields that protect all life on the surface. We've found rivers of solid rock flowing over geological timescales. We've uncovered evidence of buried continents and ancient oceans preserved in the deep mantle. Perhaps most remarkably, we've learned that this incredible alien world exists, not in some distant galaxy, but right beneath our feet. Every step you take, you're walking on the roof of the most extreme environment in the solar system. The hollow Earth theory was wrong, but it was wrong in the most wonderful way, because reality turned out to be far stranger and more beautiful than fantasy. And yet, the hollow Earth theory serves one useful purpose. It reminds us that there are still profound mysteries in the deep Earth, questions that science hasn't fully answered. While we know the Earth isn't hollow, we're still discovering surprising structures and processes in the depths. The real deep Earth continues to surprise us in ways that rival any work of fiction. Speaking of fiction, one of the most enduring thought experiments about the Earth's interior involves an imaginary journey that takes the hollow Earth concept to its logical extreme. What would happen if you could fall all the way through the planet, tunneling to nowhere? What would happen if you fell through Earth? Imagine for a moment that someone could drill a perfectly straight tunnel all the way through the Earth, from one side to the other, passing directly through the center and emerging on the opposite side of the globe. Now imagine jumping into this tunnel and falling freely under the influence of gravity. What would happen on this impossible journey to the center of the Earth and beyond? This thought experiment has captivated physicists and science fiction writers for centuries, and the answer reveals surprising truths about gravity, motion, and the structure of our planet. It's a journey that would take you through every layer we've explored: the crust, mantle, outer core, and inner core. But the experience would be unlike anything you might expect. The journey would begin much like any other fall. You'd accelerate downward under Earth's gravity, picking up speed as you descended through the first few kilometers. If we ignore air resistance, and we'd have to, since any realistic tunnel would need to be evacuated to prevent you from burning up like a meteor, you'd be falling at about 50 meters per second after just 5 seconds, roughly 100 kilometers per hour. But here's where the journey starts to become strange. Gravity wouldn't remain constant as you fell deeper. Unlike falling from an airplane where Earth's gravitational pull remains essentially the same throughout your descent, falling through the planet would involve a continuously changing gravitational field that would fundamentally alter the nature of your fall. At the surface, you experience the gravitational pull of the entire Earth, all 6 trillion kilograms of rock, metal, and everything else that makes up our planet. But as you descend into the tunnel, some of that mass is now above you rather than below you. The mass above you still exerts a gravitational force, but now it's pulling you upward, partially cancelling out the downward pull from the mass below. The mathematics of this situation, worked out by Newton himself, reveals that gravity inside a sphere increases linearly with distance from the center, but only if the sphere has uniform density. As you fall deeper, the gravitational force would initially remain roughly constant, then gradually begin to decrease as more and more of Earth's mass ends up above you. But Earth isn't a uniform sphere, it's a layered planet, with a dense iron core and lighter rocky layers. This means the change in gravity during your fall would be more complex than simple linear decrease. In the upper parts of your journey, falling through the relatively light crust and upper mantle, gravity would actually increase slightly, because you're getting closer to the dense core that dominates Earth's gravitational field. The maximum gravitational acceleration occurs not at Earth's surface, but at the core mantle boundary, 2,900 kilometers down. Here, you'd experience about 10.5 meters per second squared of acceleration, about 7% stronger than surface gravity. This is because you'd be at the closest possible approach to the dense iron core, while still having all of that core's mass pulling you downward. After passing through the core mantle boundary, gravity would begin to decrease rapidly. In the liquid outer core, the gravitational acceleration would drop steadily as more and more of the core's mass ends up above and behind you, pulling you backward rather than forward. By the time you reach the center of the Earth, the gravitational forces from all directions would exactly cancel out, and you'd experience complete weightlessness for exactly 1 instant. But you wouldn't stop at the center. By the time you reached the halfway point of your journey, you'd have been accelerating for most of the trip, and would be moving at tremendous speed, roughly 8 kilometers per second, or about 28,000 kilometers per hour. With no friction to slow you down, This enormous velocity would carry you past the center and toward the other side of the planet. Now gravity would be working against you, trying to slow you down and pull you back toward the center. But you'd have so much momentum that you'd continue rising through the other side of the Earth, decelerating at exactly the same rate you accelerated on the way down. If the tunnel extended all the way through the planet, you'd eventually emerge from the other side with exactly zero velocity, having used up all your kinetic energy climbing back up through Earth's gravitational field. Then, unless someone caught you at the exit, you'd fall back down again, beginning another complete oscillation through the planet. You'd become a human pendulum, swinging back and forth through the center of the Earth in a motion that would continue indefinitely in the absence of friction or air resistance. The timing of this oscillation is one of the most elegant results in all of physics. It turns out that the time required for one complete round trip through the Earth, falling from one side, passing through the center, emerging from the other side, and falling back to your starting point, is exactly the same as the time required for a satellite to complete one orbit around Earth at the surface. Both take approximately 42 minutes and 12 seconds. This remarkable result holds true regardless of where you drill your tunnel. A tunnel from New York to the center of the Earth and back would take the same time as a tunnel that goes all the way through to the antipodal point in the Indian Ocean. A tunnel from the North Pole to the South Pole would take the same time as a tunnel connecting any 2 points on opposite sides of the globe. This is a consequence of the deep mathematical relationship between orbital motion and harmonic oscillation. But what would the journey actually feel like? The experience would be profoundly alien, unlike any form of motion possible at Earth's surface. For most of the trip, you'd be in freefall, experiencing weightlessness like an astronaut in orbit, but you'd also be traveling through increasingly exotic environments as you descended through the layers of the planet. In the upper portions of your fall, passing through the crust and upper mantle, you'd be surrounded by solid rock heated to hundreds of degrees Celsius. If the tunnel somehow maintained its structural integrity, itself an impossible engineering challenge, you'd be falling through a tube carved through material hot enough to glow red in the darkness. Passing through the transition zone, you'd be surrounded by rock under pressures high enough to squeeze familiar minerals into entirely new crystal structures. The olivine that makes up much of the upper mantle would transform into the exotic high-pressure minerals wadzlite and ringwoodite, existing in forms that can't be stable at Earth's surface. Entering the lower mantle, you'd fall through a realm of bridgmanite and ferropyrite, minerals so exotic they were only discovered in the last few decades, and have never been found naturally at Earth's surface. The rock around you would be heated to temperatures approaching 2000 degrees Celsius, hot enough to melt copper, yet remaining solid due to the enormous pressure. The transition from mantle to outer core would be one of the most dramatic moments of the journey. You pass from solid rock into liquid metal, iron, and nickel heated to nearly 4000 degrees Celsius, and kept liquid by the combination of temperature and pressure. This liquid metal would be in constant motion, creating the currents that generate Earth's magnetic field. Falling through the outer core, you'd be surrounded by churning liquid iron, at temperatures comparable to the surface of the Sun, yet you'd still be experiencing the equivalent of gravity pulling you toward the center. The pressure around you would be over 1 million times atmospheric pressure, and you'd be falling through one of the most dynamic and alien environments in the solar system. Reaching the inner core boundary, you'd pass back into solid material, but iron under conditions so extreme that it might behave like nothing we understand from surface physics. The pressure would be approaching 4 million times atmospheric pressure, and the temperature would be nearly 6000 degrees Celsius, hotter than the surface of the Sun. At the very center, for one brief instant, you'd experience perfect weightlessness, as all gravitational forces balanced out. Then you'd begin the return journey, retracing your path through all these exotic layers in reverse order, gradually slowing down as gravity worked against your motion. Of course, this entire thought experiment is completely impossible from an engineering standpoint. No material could maintain the structural integrity needed to keep a tunnel open through the mantle and core. The immense pressures would collapse any tunnel instantly, and the extreme temperatures would vaporize any known material. Even if we could somehow create such a tunnel, it would immediately fill with molten rock and liquid metal flowing in from the surrounding layers. The thermal environment alone would be instantly lethal. Long before reaching the mantle, you'd be incinerated by temperatures hot enough to vaporize any known substance. The pressure would crush you at depths of just a few kilometers, and the radiation from naturally occurring radioactive elements would be lethal within minutes of beginning the journey. But as a thought experiment, The journey to the center of the Earth reveals profound truths about the nature of gravity, planetary structure, and orbital mechanics. It shows us that the Earth's interior follows the same physical laws that govern the motion of planets and stars, and that there are deep mathematical relationships connecting the most disparate phenomena in physics. The 42-minute journey time connects subterranean oscillation to orbital dynamics, revealing that a fall through the Earth is mathematically equivalent to a low Earth orbit. The changing gravitational field during the descent illuminates how gravity works inside massive objects, showing that the familiar inverse square law only applies outside a gravitational source. Perhaps most importantly, this impossible journey helps us appreciate just how extreme and alien the conditions inside our planet really are. The thought experiment takes us through temperature and pressure regimes that exist nowhere else in the solar system, through materials and phases of matter that challenge our understanding of physics and chemistry. The journey through the Earth reminds us that we live on the surface of what is essentially an alien world, a planet whose interior conditions are more extreme than the surface of Venus, more exotic than the depths of Jupiter, and more dynamic than anything we've discovered in our exploration of space. The most extraordinary journey in the solar system doesn't require rockets or spacecraft. It would simply require going straight down. And while we can never take this journey physically, we can take it acoustically, listening to the sounds our planet makes as it rings like a bell in response to earthquakes and other disturbances. The sound of the Earth, listening to the planet's pulse. Every few minutes, somewhere on Earth, rock breaks deep underground. The sudden release of stored stress sends shock waves radiating outward at thousands of kilometers per hour, shaking the ground and creating vibrations that travel completely around our planet multiple times. These seismic waves are quite literally the sound of the Earth. Not sound as we normally think of it, since there's no air underground to carry acoustic waves, but mechanical vibrations that cause the entire planet to ring like an enormous bell. If you could somehow amplify these vibrations and speed them up to frequencies our ears can detect, the Earth would sound like a deep, complex chord played on a musical instrument, larger than any ever imagined. Different layers would contribute different tones. The thin, brittle crust producing high-pitched pings, the thick mantle creating deep resonant hums, and the liquid outer core adding fluid, shifting harmonics that change over time. This planetary music isn't just a poetic metaphor. It's a real phenomenon that scientists have learned to decode. The science of seismology is essentially the art of listening to the Earth, interpreting the complex symphony of vibrations that constantly course through our planet's interior. Every earthquake, every landslide, every ocean wave crashing against a shore adds to this perpetual composition, creating a soundscape that reveals the hidden structure and dynamics of the world beneath our feet. The Earth's seismic song begins with the sudden rupture of rock along fault lines. When accumulated stress exceeds the strength of rock, the material fails catastrophically, snapping back to a new configuration and releasing enormous amounts of stored elastic energy. This energy radiates outward as seismic waves, pressure waves that compress and expand rock, and shear waves that shake it from side to side. But the Earth produces more than just earthquake sounds. Ocean waves create a constant background hum as they crash against coastlines and generate pressure fluctuations that travel deep into the solid Earth. Landslides, avalanches, and even large meteor impacts add their own distinctive signatures to the planetary soundtracks. Even human activities, mining explosions, nuclear tests, and large industrial operations contribute to the seismic symphony. The most remarkable aspect of these Earth sounds is how far they travel and how long they persist. When a large earthquake occurs on one side of the planet, its vibrations travel completely through the Earth and emerge on the opposite side, still strong enough to be detected by sensitive instruments. Some of these waves circle the globe multiple times, creating a resonance that can persist for hours or even days after the initial event. The Earth rings with its own natural frequencies, just like a bell or a guitar string. The fundamental mode, the deepest, slowest vibration, has a period of about 54 minutes, meaning the entire planet expands and contracts once every 54 minutes. Higher frequency modes create more complex patterns of vibration, with different parts of the Earth moving in opposite directions to create standing wave patterns. These natural oscillations, called normal modes, were predicted by theory long before they were actually observed. It wasn't until the development of extremely sensitive seismometers in the 1960s that scientists could finally detect these subtle planetary vibrations. The frequencies and patterns of normal modes provide information about Earth's internal structure that can't be obtained any other way, revealing details about density variations, elastic properties, and even the rotation of the inner core. The quality of different Earth sounds varies dramatically depending on their source and the path they take through the planet. Shallow earthquakes in the crust produce sharp, high-frequency sounds that don't travel very far before being absorbed by rock. Deep earthquakes in the mantle produce longer period waves that can circle the globe multiple times. The deepest earthquakes, occurring in subducting slabs 600 kilometers or more below the surface, create some of the purest tones in the Earth's seismic symphony. The liquid outer core acts like a massive acoustic filter, blocking shear waves but allowing pressure waves to pass through with altered velocities and frequencies. This creates a distinctive acoustic signature that allows seismologists to identify when waves have passed through the core. The solid inner core adds its own acoustic properties, creating reflections and refractions that reveal its size, density, and even its rotation rate. Different materials in the Earth have different acoustic signatures, like instruments in an orchestra. Dense materials like iron in the core transmit high-velocity waves that arrive early at distant seismic stations. Light materials like the crustal rocks transmit slower waves that arrive later. Hot materials tend to transmit waves more slowly than cold materials, allowing seismologists to map temperature variations in the deep Earth. The absorption of seismic waves also tells us about the physical state of materials deep in the Earth. Solid rock transmits waves efficiently with little loss of energy. Partly molten rock absorbs more energy, creating distinctive patterns of wave attenuation. The transition from solid to liquid at the outer core boundary creates one of the most dramatic changes in wave propagation properties anywhere in the planet. Recent advances in seismic instrumentation have revealed ever more subtle aspects of the Earth's acoustic behavior. Modern seismometers can detect ground motions smaller than the width of an atom, allowing scientists to record vibrations from earthquakes so small they wouldn't be felt by humans. Networks of these ultra-sensitive instruments have revealed that the Earth is never truly quiet. It's constantly humming with vibrations from ocean waves, atmospheric pressure changes, and even the gravitational effects of the sun and moon. The ocean plays a particularly important role in generating Earth sounds. Ocean waves create a constant background of seismic noise called microseisms, which show up on seismograms around the world as continuous low-level vibrations. During large storms, the interaction between ocean waves can create powerful pressure pulses that propagate into the solid Earth and can be detected thousands of kilometers away from the storm itself. Climate change is actually changing the Earth's acoustic signature. As weather patterns shift and ocean temperatures rise, the patterns of ocean wave generation are changing, altering the background seismic noise that serves as a constant soundtrack to our planet's existence. Some scientists think these changes in seismic noise might eventually serve as indicators of global climate patterns. The Earth's acoustic properties also change over time in response to internal processes. The gradual cooling of the planet affects wave velocities throughout the interior. The growth of the inner core changes the acoustic properties of the deep Earth. Even the motion of tectonic plates alters the paths that seismic waves take through the planet, creating temporal variations in the Earth's acoustic signature. Artificial sounds added to the Earth's natural symphony have provided important insights into planetary structure. Nuclear weapons tests during the Cold War created powerful seismic signals that were detected around the world, providing data about deep Earth structure. More recently, controlled explosions for oil and gas exploration have created detailed acoustic maps of crustal structure in specific regions. The study of Earth sounds has revealed that our planet is far more acoustically complex than early seismologists ever imagined. The simple picture of uniform layers with distinct boundaries has been replaced by a more nuanced understanding of gradational changes, complex three-dimensional structures, and dynamic processes that create temporal variations in acoustic properties. Perhaps most remarkably, scientists have learned to use the Earth's natural acoustic behavior to detect and study events that produce no other observable signals. The gradual motion of magma beneath volcanoes creates subtle changes in seismic wave propagation that can be detected long before any eruption occurs. The slow slip of fault segments that don't produce felt earthquakes can be identified through changes in the acoustic properties of the surrounding rock. The Earth's acoustic signature also extends beyond our planet. Some of the most powerful earthquakes create vibrations strong enough to disturb the atmosphere and even affect satellites in orbit. The 2011 Tohoku earthquake in Japan created atmospheric pressure waves that were detected by GPS satellites, showing that major seismic events can literally shake the entire Earth atmosphere system. As we listen to this perpetual planetary symphony, we begin to understand that the Earth is not a silent, static object, but a dynamic, resonating system that's constantly making music. Every earthquake adds a new note to this composition. Every ocean wave contributes to the rhythm. Every landslide, every volcanic eruption, every shift in the deep mantle adds its own voice to the choir. The Earth's song is ancient. It's been playing since our planet formed 4.5 billion years ago. But it's also constantly evolving. As internal processes change the acoustic properties of different regions, and external forces add new sources of vibration. It's a composition without a composer, a symphony without a conductor, a musical performance that will continue as long as our planet exists. And hidden within this acoustic complexity is evidence of motion at the very center of our world. The surprising discovery that the Earth's core isn't as stable and stationary as we once thought. The center that moves. How Earth's core isn't still. Have you ever watched a sleeping cat? The way its chest rises and falls in a gentle rhythm. The way its ears occasionally twitch at sounds we can't hear. There's something profoundly peaceful about witnessing that quiet motion, that life continuing, even in stillness. But here's the beautiful paradox. What we call stillness often contains the most extraordinary movement of all. Imagine for a moment that you could shrink yourself down and journey to the very heart of our planet. You might expect to find something solid, something fixed and permanent, like the foundation stone of an ancient cathedral. But what you'd discover instead would be far more wondrous. A heart that beats with liquid metal. A center that dances with currents older than the continents themselves. The Earth's core isn't still. In fact, it's one of the most dynamic places in our entire solar system. A realm where molten iron swirls in patterns so complex they'd make a master choreographer weep with envy. This is the story of motion hidden in the deepest darkness, of rivers that flow without banks, of a dynamo that's been running for over 4 billion years, without ever needing maintenance. Let's begin with what seems like a simple question. What does it mean for something to be still? When you're sitting quietly, reading these words, are you truly motionless? Your heart is beating roughly 70 times per minute, pushing blood through 60,000 miles of vessel. Your lungs are expanding and contracting, drawing in air that travels from your nose to tiny sacs called alveoli in about 15 seconds. Your brain is firing electrical signals faster than lightning, processing thousands of thoughts and sensations every moment. The stillness, we discover, is often an illusion of scale and time. What appears motionless from one perspective reveals itself as gloriously active from another. And nowhere is this more dramatically true than in the depths of our planet. The Earth's core exists in two distinct layers, like a cosmic egg, with two different kinds of yolk. The inner core, about 760 miles in radius, is solid iron and nickel, compressed under pressures that would crush diamonds into powder. But surrounding this solid heart is the outer core, a layer of liquid metal, nearly 1,400 miles thick. And this is where the magic happens. In this outer core, temperatures soar to over 9,000 degrees Fahrenheit, hotter than the surface of the sun. Under such extreme conditions, iron doesn't behave like the metal we know from our everyday world. It becomes a fluid, flowing like honey. But honey with the peculiar property of conducting electricity better than the copper wires in your home. Now, here's where the story becomes truly extraordinary. This liquid metal isn't just sitting there glowing quietly in the darkness. It's moving, swirling, churning in vast currents that make our mightiest ocean currents look like gentle streams. These flows are driven by heat, escaping from the Earth's center, creating what scientists call convection. The same process that makes soup bubble in a pot, but operating on a scale that spans continents. Picture, if you will, towering columns of molten iron, rising from the depths like invisible tornadoes, carrying heat upward for hundreds of miles before cooling and sinking back down. These currents don't move in simple circles, though. They twist and spiral, influenced by the Earth's rotation, creating patterns so complex that supercomputers struggle to model them accurately. And here's the truly magical part. As these electrically conducting currents flow through space, they interact with magnetic fields that already exist, strengthening them, twisting them, and generating new ones. It's like having a vast electrical generator hidden at the center of our world, one that creates the magnetic field that protects us from deadly solar radiation and guides compasses around the globe. This process, called the geodynamo, is one of nature's most elegant feedback loops. The flowing metal generates magnetic fields, and those magnetic fields influence how the metal flows, which changes the magnetic fields, which affects the flow round and round, in an intricate dance that's been continuing for billions of years. But the Earth's core doesn't just move in predictable patterns. It has moods, like a living thing. Sometimes the magnetic field it generates is strong and stable. Sometimes it weakens dramatically, or even flips completely, with magnetic north becoming magnetic south. These reversals happen on average every few 100,000 years, though the timing is wonderfully unpredictable, like trying to guess when a cat will suddenly decide to sprint across the room for no apparent reason. Scientists have discovered that the inner solid core isn't perfectly centered within the outer liquid core. It can actually move around slightly, wobbling like a ball bearing in a bowl of thick syrup. Even more remarkably, the inner core appears to rotate at a slightly different speed than the rest of the planet. Sometimes faster, sometimes slower, as if it's dancing to its own rhythm. Recent research has revealed something even more surprising. The flows in the outer core aren't random. They form organized patterns, jet streams of molten metal that can persist for decades or centuries. These jets can suddenly accelerate or change direction, causing rapid changes in Earth's magnetic field that we can detect at the surface. It's as if the planet's heart has a pulse that occasionally skips a beat or suddenly races with excitement. The temperature differences that drive these flows are surprisingly small, just a few degrees difference between the inner boundary and outer boundary of the outer core. But when you're dealing with a layer of liquid metal nearly 3,000 miles across, even tiny temperature differences can drive currents carrying more energy than all of humanity uses in a year. And the beautiful irony is that this motion, this constant churning and flowing deep beneath our feet, is what keeps our surface world stable. Without the magnetic field generated by the core's movement, Earth's atmosphere would be slowly stripped away by solar wind. Like what happened to Mars billions of years ago. The motion that seems chaotic and unpredictable is actually what makes life possible on the surface. The study of Earth's core requires us to become detectives, piecing together clues from seismic waves, magnetic field measurements, and laboratory experiments that recreate the extreme conditions thousands of miles below. We can't directly observe these hidden rivers of metal, but we can feel their effects, in the way compass needles point north, in the aurora that dance across polar skies, in the subtle changes in Earth's rotation that atomic clocks can detect. Sometimes on a quiet night, when the world seems perfectly still, I think about that hidden heart of our planet, beating with currents of liquid fire, generating the invisible shield that protects us all. It's a reminder that the most important movements often happen in the deepest silence, that stillness is often just motion too profound and too patient for us to immediately perceive. The center that moves, it's been flowing since before the first life appeared on Earth, and it will continue long after the last star fades from the sky. In its restless motion we find one of the universe's most beautiful paradoxes, that sometimes the most stable thing you can do is never stop moving at all. Why we'll never reach it. The uncrossable barrier below. There's something humbling about standing at the edge of the ocean, watching waves roll toward the horizon until they disappear into the curve of the Earth. No matter how far ships have sailed or how deep submersibles have dove, there's always more ocean beyond our reach, more mystery waiting in the depths. But even the deepest ocean trench is like a shallow puddle compared to the journey to Earth's core, a journey that represents, perhaps, the ultimate, unreachable destination. Imagine telling someone from a century ago that humans would walk on the moon, that we'd send robots to Mars, that we'd capture images of galaxies billions of light years away. They might have thought you were dreaming impossible dreams, yet here we are, having achieved all of that and more. We've conquered the sky, reached into the cosmos, and peered into the quantum realm. But there's one place that remains as inaccessible today as it was to our ancestors who first wondered what lay beneath their feet, the center of our own planet. The deepest humans have ever penetrated into the Earth is about 7.5, the depth of the Kola super-deep borehole in Russia, a Soviet-era project that took over 20 years to drill. To put that in perspective, if the Earth were an apple, we haven't even penetrated the skin. The core lies nearly 4,000 miles below our feet, separated from us by barriers so formidable they make the challenges of space travel seem almost trivial by comparison. Let's start with the most obvious obstacle. As you descend into the Earth, temperature rises by about 77 degrees Fahrenheit for every mile of depth. That might not sound like much at first, but the mathematics becomes terrifying quickly. By the time you reach just 25 miles down, you're dealing with temperatures hot enough to melt lead. At 100 miles depth, you're encountering temperatures that would vaporize most metals we know, but the core exists at temperatures exceeding 9,000 degrees Fahrenheit, hotter than the surface of the sun. No material we've ever created can maintain its structure at such temperatures. The strongest steel would become a gas long before reaching even a fraction of that heat. Even our most advanced ceramic composites, designed to withstand the extreme conditions of spacecraft re-entry, would dissolve like sugar in hot coffee. And temperature is just the beginning. Pressure increases even more dramatically with depth than temperature does. At the surface, we live under 1 atmosphere of pressure, about 14.7 pounds per square inch. Every mile you descend adds roughly another atmosphere of pressure. By the time you reach the core, you're dealing with pressures over 3 million times greater than what we experience at sea level. To understand what that means, imagine trying to compress a car down to the size of a marble while keeping all the metal intact. The forces involved are so immense that they change the fundamental behavior of matter itself. Under such pressure, even empty space becomes compressed. The very atoms that make up any material we might use for a journey vessel would be squeezed so tightly that electrons would be pushed into different orbital patterns, potentially changing the chemical properties of elements themselves. These aren't just engineering challenges, they're fundamental limitations imposed by the laws of physics. It's not that we haven't yet developed the right materials or technologies, it's that the conditions at Earth's core exist beyond the realm where normal matter can maintain its structure and properties. But let's imagine for a moment that we somehow solved the heat and pressure problems. Perhaps we developed some miraculous material that could withstand the journey, or maybe we sent down some kind of energy-based probe instead of physical matter. Even then, we'd face obstacles that seem almost designed to keep us away from the core. The journey down would take us through the mantle, a layer of rock so hot it behaves more like extremely thick honey than solid stone. This semi-liquid rock is in constant motion, with currents and flows that could easily carry any object off course. It would be like trying to navigate through an ocean of molten glass, where currents move at the speed of fingernail growth. But with the power to crush mountains, even if we could somehow track our probe through this environment, the very act of drilling or melting a path downward would be constantly undone by the flowing rock around it. Imagine trying to dig a hole in water. The moment you remove material from one spot, more flows in to fill the gap. The mantle's convective movements would heal any passage we created almost as quickly as we made it. Then there's the question of power and communication. Any device making the journey to the core would need to carry its own energy source. Since no cable could survive the trip down or provide reliable power across such distances through such extreme conditions. But what power source could operate at 9,000 degrees Fahrenheit under crushing pressure? Chemical batteries would fail instantly. Nuclear power sources would face challenges we can barely imagine as their very atomic structure was altered by the extreme environment. Communication presents equally daunting challenges. Radio waves that work perfectly in space or even deep underground would be absorbed or scattered by the dense, electrically conductive materials surrounding the core. Even if we could establish communication, the signals would have to travel through thousands of miles of interfering material, arriving distorted beyond recognition if they arrived at all. Perhaps most poetically, the very properties that make Earth's core so fascinating are the same ones that make it unreachable. The magnetic field generated by the core's motion creates powerful electromagnetic interference that would disrupt any electronic systems. The convective flows that drive our planet's geological activity would batter any object trying to pass through them. The heat that powers our planet's magnetic dynamo would destroy any vessel we sent toward it. It's as if the Earth's core exists behind a wall made of physics itself, not just one barrier, but layer upon layer of increasingly impossible conditions. Heat that melts everything we know, pressure that crushes atoms, flows that reshape matter, and electromagnetic fields that scramble any attempt at communication or control. But there's something beautiful about this impossibility. In an age where technology seems to make everything achievable, where we're constantly told that any barrier can be overcome with enough engineering and determination, the Earth's core remains genuinely unreachable. It's a reminder that some mysteries are meant to stay mysterious, that some places exist beyond our direct experience by the very nature of what they are. This doesn't mean we can't study the core. We've learned tremendous amounts through indirect methods. Seismic waves from earthquakes travel through the Earth like sound waves through a building, and by carefully analyzing how these waves bend, speed up, slow down, and reflect off different layers, we can map the interior structure of our planet with remarkable precision. It's like being able to understand the layout of a house by listening to how sounds echo through its rooms. We can recreate core conditions in tiny samples using diamond anvil cells and laser heating, squeezing microscopic amounts of material to core pressures and temperatures for brief moments. We can run sophisticated computer simulations that model the behavior of matter under extreme conditions. We can study Earth's magnetic field and how it changes over time, reading the signature of the core's behavior written in invisible lines of force that surround our planet. In some ways, these indirect methods teach us more than direct observation ever could. They require us to become detectives, piecing together clues, developing theories, testing predictions. They force us to understand not just what the core is, but how it works, how it influences everything else, how it fits into the grand symphony of planetary processes. The unreachable core serves as a powerful metaphor for the nature of knowledge itself. Some truths can't be grasped directly. They must be approached with patience, creativity, and respect for the barriers that protect them. The core's inaccessibility doesn't diminish our understanding. It deepens it, making every insight we gain more precious because it was earned through careful reasoning rather than simple observation. And perhaps that's the most beautiful aspect of this unreachable realm. In a universe where we've walked on other worlds and peered back to the beginning of time, the center of our own planet remains forever beyond our direct reach, a reminder that home still holds mysteries, that the most familiar places can harbor the most extraordinary secrets. The uncrossable barrier below isn't just about physics and engineering limitations, it's about the profound humility that comes from recognizing that some frontiers will always remain frontiers. Some mysteries will always inspire wonder precisely because they can never be fully conquered. In the unreachable depths beneath our feet lies perhaps the last truly inaccessible place in our immediate cosmic neighborhood. And in its permanent mystery, we find a kind of eternal invitation to keep dreaming, keep theorizing, and keep marveling at the extraordinary planet that is our home.